The rolling is around the longitudinal axis. Yeah, I hammer that one home because on probably 90% of the exams there will be a question, pardon me, about which control, about which axis, or in which direction does the aircraft move around which axis. So stick them in your head. Yeah, so that's your page 5, your basic axes. Page 6, the sketch there. The ailerons are located at the furthest outboard position away from the center of gravity to give us the greatest rolling moment. Yeah. So the ailerons move up and down, as you're well aware, and they're located on the wings. Yeah. Again, highlighting the fact that the ailerons provide lateral control about the longitudinal axis. So the aileron operated from the control wheel. Yeah, aileron moves up and down in tandem with its opposite number. As one moves up, the other one moves down. The elevators located on the horizontal tailplane, and they move as one unit. Yeah, they provide a longitudinal control around the lateral axis, so we'll call that pitching control. Again, operated from the cabin via control cables. The elevators will move up and down in unison. Yeah, so whatever the left-hand one does, the right-hand one does. The rudder, located on the vertical stabilizer, the back of the vertical stabilizer. Again, the rudder is going to give us directional control about the normal axis, and that is known as yawing. Yeah, and the rudder operated from control pedals in the flight deck, and the rudder is going to move left and right, and we're going to get directional response from the aircraft. Dead easy. Dead easy. Yeah, control surfaces, as we said, placed the furthest point that we can from the center of gravity to give us the best possible turning moment for the aircraft. How they're going to do that? Yeah, principle's the same. Yeah, the control surfaces placed at the maximum distance from the CG produce the greatest possible turning moment. The control surfaces, when we move them, create a convex camber on one side of the main surface and a concave camber on the other. Yeah, pressure reduced on the convex camber, increased on the concave, and that causes the control surface to move in or the main surface to move in the opposite direction to which control surface is moved. Yeah. When we say that the control surface movement is instinctive, yeah, if the pilot moves the stick to the left, the aircraft is going to turn to the left. If he pushes the stick forward, the aircraft's going to go nose down. If he pushes a pedal left or right, the aircraft is going to turn in the direction of that pedal. So your control surface normally sitting nice and fared with the main surface. If I move the control surface, yeah, what I'm doing is creating that concave on one side and the convex on the other. Yeah, we get a reduction in pressure around the convex, increase in pressure around the concave, and that is going to create movement. Yeah, so in this case, the positive pressure, negative pressure, the positive pressure is going to move the main surface upwards. So the main surface is moving in the opposite direction to the control surface. Counter to that, yeah, if I move the control surface in the other direction, I'm creating a concave. On the upper surface, I'm controlling a convex on the lower surface. The positive pressure, the negative pressure is going to cause the main surface to move downwards. Yeah, so again, it's moving in the opposite direction to the control surface. Dead easy. Anybody got any problems there? Yeah. Potential movement, yeah, page 7, potential range of movement or travel in the same in both directions, but elevators normally have greater up movement than down movement. Yeah. The difference in movement provides the extra force when pulling out of a dive or a glide and keeps the tail down when the aircraft is taxiing. Okay, so whack a highlighter through that. The elevators usually have a greater up movement than a down movement. And the reason for that, so we can pull out of a dive or a glide. The aileron travel depends on the. We'll look at aileron travel as a separate item in a moment or two. Yeah. For structural reasons, to prevent overstressing the aircraft, we're going to limit the range of movement of the control surfaces. And to limit that range of movement, we're going to put mechanical stops at the control surface and at the cockpit end of things. Okay, right. Roll control then. Yeah. We said that lateral or rolling control about the longitudinal axis is provided by the ailerons. And the aileron's control surface is hinged to the rear of the main planes. Yeah, so the aileron's out, hinged to the rear of the main planes. Control column move to the left or the right. Yeah. Control column or the control wheel, as it says in the notes. The aileron's going to move in the opposite direction. So if I move the control column to the right, the right-hand aileron's going to move up, the left-hand aileron's going to move down. Yeah, that again changes the camber of the wing, and because we're changing the camber of the wing, we're going to create lift. Yeah, so as I turn the stick to the right, yeah, the left-hand aileron moves down, and that is turning the aircraft to the right. I'm creating more lift. That wing's going to lift up. On the opposite wing, the opposite aileron's going to be deflected up. That's going to create drag. It's going to reduce the lift that's being generated. So now the aircraft is going to turn in the right-hand direction. Yeah. If I move the control column to the left, obviously the opposite's going to happen. Yeah, the left-hand aileron would go down, the right-hand aileron would come up. More lift on the left and the right-hand side, so it'd turn the aircraft to the left. Happy days. Happy days with that. All right, one of the problems that can arise is a thing called aileron drag. So when we move an aileron down, we're increasing the angle of attack on that part of the wing where that aileron's fitted. That's going to create lift. And as it creates lift, it's also creating drag. The opposite aileron, the upgoing aileron, is going to decrease its effective angle of attack. And because it's decreasing the lift, it's decreasing the amount of drag that we're generating. So the downgoing aileron, a lot of lift, a lot of drag. Upgoing aileron, a lot less lift, a lot less drag. And that tends to cause the aircraft to yaw in the direction of the upgoing wing. And that tendency of the aircraft to try and yaw around is known as aileron drag or adverse aileron yaw. Yeah. Everybody see how that's working? Yeah, more lift, more drag, less lift, less drag. Yeah, so now because you've got less drag on the downgoing wing than you have on the upgoing wing, the aircraft is going to try to turn in the direction of the upgoing wing. So it's going to try and turn into against the direction we're turning. That's known as aileron drag. The problem with aileron drag arises when we try to do the same maneuver at low speeds. Yeah, so that at low speed, the downgoing aileron will produce the same effect as increasing the angle of attack. Because you're increasing the angle of attack, the effective angle of attack, if you're traveling at low speed, there's a possibility that you could stall the wing. If we stall the wing, yeah, we're going to lose all the lift on that, wing. That wing will just drop suddenly, and then the aircraft is going to be very difficult to recover. Yeah, so tip stall, yeah, is caused by aileron drag at very low speed. Downgoing aileron increases its angle of attack. That increase in angle of attack could cause the wingtip to stall. Stall at the wingtip, the wing's going to drop very, very quickly. Yeah, and because that wing's dropping, it makes control of the aircraft very difficult. All okay with that? Yeah. So what we want to do is to try and prevent that wingtip from stalling. And just before I do that, will you excuse me just 2 minutes? I've just got to nip down and reset my heating. The heating's gone off and it's bloody freezing in here. I won't be a second. Sorry about that. I thought it was getting cold. And we had snow last night, and looking out at the snow, that makes you feel even colder. Right, so preventing tip stall then. Yeah, tip stall, low speed turn. Yeah, the wingtip would drop very, very rapidly. You'd end up going in the opposite direction of what you want. Aircraft very difficult to control, difficult to recover. So there are different methods of reducing the effect of that tip stall. We can. I'll go through each of these, but as it notes in the book there, again worth a highlight at page 10. The different methods: differential aileron, freeze type ailerons, slotted ailerons. We can use spoilers, and we can use washout. Most aircraft there'll be a combination of methods. Yeah. So what we're looking at with differential aileron, yeah, what we're doing is changing the amount of travel that we're going to get on the ailerons as they move. We're going to get more movement on the upgoing aileron than we are on the downgoing aileron. Yeah, you down travel less than the up travel. And that means that as the aircraft's manoeuvring, because you've got more movement on your upgoing aileron, you're going to create more drag on that upgoing side. the side of the it talks about upgoing wings, downgoing wings. Yeah, the aileron in the inner wing, in the turn will produce more drag than the other aileron, and that's going to even things out, and that's going to help reduce the possibility of tip stall in a low speed turn. Let's go back to that one. Yeah, so if I reduce the movement on the downgoing aileron, increase the movement on the upgoing aileron, when I go into the turn, I'm giving myself more drag on the upgoing aileron, less drag on the downgoing aileron. So we're sort of reducing the possibility of stalling the tip as we move around. And that's what we mean by differential aileron, just the difference in movement. But remember, you're going to get less movement on the downgoing aileron than you are on the upgoing. When we come to the flying controls themselves, we'll look at how we're going to embody these things mechanically on the aircraft. So don't worry about that just yet. But just highlight the fact that there's going to be less movement on the downgoing aileron than there is on the upgoing one. Freeze type ailerons. Again, the freeze type aileron has got the hinges set back in the leading edge. So what? Yeah.
Which aileron is most commonly used? Which you have already said.
Yeah, we use a combination of the different methods. So most aircraft will have differential aileron.
Okay, thank you.
Yeah, most aircraft will, but like we said back at page 10.
10, yeah.
Yeah, that it's common practice for a combination of these methods to be used on the same aircraft. So, if I've got an aircraft, it'll have probably differential aileron. I think most of them have that. It might have the slotted ailerons fitted to it. It might have spoilers. Again, it'll probably have washout. Most aircraft have washout. So it's not just one method. We're going to use a combination of the methods.
Okay.
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 Your freeze type aileron, the aileron, the hinges are set back in the leading edge. So when the ailerons are operated, the leading edge of the upgoing aileron protrudes below the wing, and that creates that additional drag. Leading edge of the downgoing aileron doesn't protrude above the wing, so it's having the same effect really as the differential aileron, because the upgoing aileron is creating more drag. So it's having the similar effect. The downgoing aileron isn't creating that drag because it's the hinges aligned, if you like, with the upper surface. So if I move the ailerons, the upgoing aileron, the nose of that upgoing aileron protrudes into the airflow, and like we say, that's going to create a bit of drag. The downgoing one doesn't. So that is what they call the freeze type aileron. If truth be told, the illustration you've got on page 11 is probably better than the one that's on the slide. But there we go. Freeze type aileron. Sits nice and flush when it's in its neutral position. The downgoing aileron again will just create that nice camber, but the upgoing aileron, the nose will protrude into the airflow and create that drag. So we're reducing the possibility of the tip stall at low speeds. The slotted aileron, when that's lowered, a slot's formed between the wing and the leading edge of the aileron. The air will race through that slot, yeah, and it will energize the boundary layer. We talked about energizing the boundary layer before. Yeah, so the air from the low surface accelerates through the stop, reduces the turbulence over the aileron by keeping that boundary layer attached. It's reducing drag, increasing the lift on the outer wing in the turn, and helping to turn the aircraft. And again, at the same time, yeah, we're reducing the chances of tip stall. So your aileron nice and happy in the neutral position. The downgoing aileron air is going to flow through that slot and over the top, marrying up with the air coming across the aerofoil. So we're just creating that that bit more lift, less drag. The upgoing aileron, yeah, is going to create more drag. So again, we're evening things out, if you like. Yeah, so reducing that possibility of tip stall. Spoilers. It says aileron drag may be reduced by fitting a spoiler on the top surface of the wing and front of the aileron. That's going to assist the upgoing aileron. It's going to increase the drag on that portion of the wing. Yeah. Some aircraft they don't actually fit ailerons and they just provide roll control by the spoilers themselves. Yeah. Additional roll control sometimes provided by differential tailplane. We'll kind of look at those a bit later on. Spoilers, as we should be aware from our construction, spoilers are just flat panels that live on the top of the wing in front of the ailerons, and the spoilers will raise upwards. They'll increase the drag on the downgoing wing, yeah, which is going to assist the ailerons maneuver the aeroplane. The other method we can use is what they call washout. Yeah, and washout is the change of the incidence angle along the span of the wing. And what we're going to do is start with a large angle of or a relatively large angle of incidence at the root of the wing. Yeah. And there's going to be a deliberate twist in the wing to reduce the angle of incidence at the wing tip. Yeah, that now means as we're manoeuvring the aircraft, the inboard portion of the aircraft wing is going to have a larger angle of attack in the turn. Because it's got a larger angle of attack in the turn, it's the root that's going to stall first. Yeah. Because we've reduced that incidence at the wing tip, yeah, we're going to get a higher angle of attack in the maneuver, or to stall the wing tip, I should say, we'd need a higher angle of attack. Yeah, so by deliberately twisting the wing, yeah, now as we maneuver the aeroplane, the angle of attack in the wing has got to be increased greatly before we get to that stall point. Yeah, and that deliberate twist of the angle of incidence known as washout. Not a fantastic picture, but the best one I could find. You can see the angle of incidence at the wing root on this aircraft. That's your centre line there. You've got quite a high angle of incidence there, but you can see that the angle of incidence at the wing tip, yeah, is a lot greater than a lot less than the angle of incidence at the wing root. Go back, go there,
Jim,
go there. Yeah.
Its angle of incidence is fixed, right?
Yeah, the angle of incidence is the angle at which the if that's your That's your aeroplane. The angle of incidence is the angle at which the wing is physically mounted to the fuselage. Just give me a second.
Yeah, I mean to say that given figure in previous slide, do you have to remember that tip angle of incidence and the root angle of incidence?
No. The angle of incidence, we're going back to our aerodynamics now. Yeah, the angle of incidence is the angle at which the again, that's your aircraft. I don't know why it's doing that. And the wing is going to be mounted at a fixed angle to the fuselage, and that's where the wing is physically bolted on. Yeah, that angle is the angle of incidence. The angle of attack is the angle at which the wing meets the airflow. Yeah, so that why does it do that? Houston, we have a problem. Let's see if it does it with a different color. Yeah, so yeah, for some reason it's like looking at one of those heart monitors, isn't it? Keeps spiking. Yeah, aeroplane. Angle of incidence, the angle at which the wing is mounted to the fuselage. That angle is normally around 3.5 degrees. Yeah, and the reason for that is you go back to your aerodynamics, your minimum drag speed, and all the rest of it. Your best lift drag ratio. Yeah, the angle of attack is the angle at which the wing meets the airflow. So that the angle of attack is the angle between the chord line of the wing and the relative airflow. So if I put the aircraft at that sort of angle, I've got my angle of incidence, but the angle at which the wing is meeting the airflow is the angle of attack. I apologize for the drawings. I apologize for the slides. Not something. I'm better with a whiteboard. But as back to your question, do you need to remember the half degree? No, just know that the angle of incidence is greater at the wing root than it is at the wing tip.
Okay, got it. Thank you.
Yeah.
Okay. Thank you.
Anybody else there? Before we move on. No. Okay then. So that's the aileron side of it. The aileron giving us roll control about the longitudinal axis. We've got adverse yaw that the ailerons can produce, and that adverse yaw, if we try to maneuver the aircraft at low speeds, could give us tip stall. So we've got those different methods of, shall we say, simplistically, we're evening out the drag across the wings, and because we're evening out that drag, we're reducing the chances of the tip stalling. We're going to use a combination of the different methods on the aircraft for that tip stall prevention. So depending on the aircraft type, depends on the methods that they use. Pitch control then. Yeah, your pitch control is movement about the lateral axis, and that movement about the lateral axis is provided by the elevators. The elevators are hinged control surfaces at the back of the horizontal stabilizer. If I pull the stick back, yeah, the elevator is going to rise. As the elevator rises, as we saw before, we're creating that concave on the top of the wing, pressure pushing down. That's going to push down on the tail. It's going to bring the nose of the aircraft up. Opposite effect, if I push the stick forward, yeah, the elevator is going to move in a downwards manner, and that's going to create a concave surface, which in turn, rising pressure, is going to push the tail up. As the tail goes up, the nose comes down. Hence, you've got your instinctive movement there. Yeah. So we're pitching about the lateral axis, stick forward, stick back, moving the elevators. Yeah, again, just an example of how your elevators are affecting your pitch. Stabilators, it talks about stabilators in the book, and the stabilator may also be known as the all-moving or the all-flying tailplane. Yeah, that provides stability control and trim. Smaller types of aircraft, the stabilator moves through the use of an anti-balance tab. Stabilator hinged to the fuselage. Yeah, so it's just a one-piece tailplane hinged to the fuselage. When I move the control column, the whole stabilator moves. Yeah, pull the stabilator back. The angle of incidence is going to change on the stabilator, which in turn is going to alter the attitude of the aeroplane. So it's going to pitch, depending on which way I push the stick. I'm going to pitch up or pitch down. You can have an anti-balance tab hinged to the trailing edge of the stabilator. That tab connected by a linkage to the fuselage. The stabilator moves. The tab moves in the same direction as the stabilator trailing edge. Should the angle of incidence change, the anti-balance tab will move in the same direction as the stabilator trailing edge, and that will produce a correcting force to bring the stabilator back into its original line. Yeah. So your anti-balance tab, or it calls it an anti-servo on here. Yeah, there's a linkage connected to the fuselage at some point. So as I move the stabilator, because of that linkage, the anti-servo tab is going to move as well. Yeah, so your anti-balance tab on this one, shown at the back of the stabilator. Yeah, move the stick forward, move the stick back. Yeah, as the stabilator moves, the anti-balance tab is going to move, and that's going to try to push the stabilator back to its original position. Again, move the stick in the opposite direction. The servo tab is going to move, and again, as the stabilator is moving, that's going to try to push the thing back. Yeah, so the anti-balance tab connected by a linkage to the fuselage structure. When the stabilator moves, the tab moves in the same direction. For stick-free stability, the stabilator is positioned with the anti-balance tab in neutral. When it talks about stick-free stability, yeah, it can just fly along with your hands off. Everything's in neutral, so that there should be no pitching effect at all. Yeah. Should the angle of incidence change, as we've just seen, the anti-balance tab will move in the same direction as the stabilator trailing edge, and that will produce a correcting force to bring the stabilator back to its original position. So when we're flying stick-free, hands-free, let's, for example, say we go through a bit of turbulence. Yeah, if the stabilator moves, then the anti-balance tab will automatically bring it back to its neutral position. The other thing with the anti-balance tab, as the pilot's moving the stick, it's going to create a resistance to the movement by the pilot, so that resistance is helping to prevent the pilot from overstressing the aeroplane, from over-maneuvering the aeroplane. We'll look at anti-balance a bit later on, but again, it's quite useful. So having the anti-balance tab there, we're flying along, fat, dumb, and happy. Little bit of turbulence. The stabilator moves. The anti-balance tab is going to bring the thing back in line and just recover the aircraft. Pilot moves the stick. The whole stabilator is going to move. And by moving the whole stabilator, that's going to move the aircraft. That's going to pitch the aircraft. And again, the more we try to move the stick, the anti-balance tab is going to create that resistance, and that's going to prevent the pilot from overstressing the aeroplane.
Jim.
Yeah.
This anti-balance tab is a part of the elevator or trailing edge of elevator?
Not the elevator, the stabilator. The stabilator, the whole tailplane, the whole tailplane moves. There's not a separate elevator on it.
Okay.
You see on this little aeroplane, you've got your horizontal stabilizer, and at the back of the stabilizer, we've got the elevator. With a stabilator, the whole tailplane is the elevator. So it's the whole stabilator that moves up and down to give us pitch control. At the back of the stabilator is where we have this little anti-balance tab. Yeah?
Okay, Jim.
You sure?
Hello, Jim.
Yeah.
Hello.
This anti-balance tab and anti-servo tab, they both are same thing?
Yes. It's just terminology.
Okay, thank you.
So this anti-balance tab is only applicable to stabilator?
No.
Okay.
No. In this case, when we're talking about pitch control, all we're saying is that the stabilator may or may not have an anti-balance tab fitted to it. The main purpose of the anti-balance tab is to provide feel for the pilot, and the more he tries to move the control surface, the more resistance he's going to get. But by having that anti-balance tab there, when we're flying hands off, that's in neutral position. It's faired with the stabilator. If the stabilator moves, the anti-balance tab's going to move as well, and that's just going to provide a correcting force. So if we're flying along, a little bit of turbulence moves the stabilator for whatever reason, then the thing will correct itself and go back to the neutral. Not all stabilators have anti-balance tabs. The bulk of them do, but not all of them do. Any more questions there? Right, for your larger aircraft, during cruise, because of the center of gravity, the center of lift, the aircraft is going to have a tendency to try and fly nose down. Center of lift behind the center of gravity. That center of lift is going to try to push the nose down. So what we need to do is to counteract that by putting a down force on the tail to keep us straight and level when we're away in the cruise. Now, what we could do is raise the elevator on the stabilizer on the horizontal tailplane, raise the elevator, and that would provide that download. But by doing that, yeah, we're going to create a lot more drag. And by creating drag, we're going to need power to overcome that, thrust to overcome that. That extra thrust is going to burn fuel, so it becomes quite expensive. And the other thing with having the tailplane, imagine that's your horizontal stabilizer. Yeah, want to put a downforce on, so I'm going to have to move the elevator up. Yeah, that is going to create drag, overcome the drag, more thrust needs more fuel. So that's going to be work out expensive eventually. But the other thing, if you've got the elevator sticking up in the airflow all the time, it's going to start to create structural problems around the hinge area. So it's a lot easier, yeah, if we could just move the whole tailplane, yeah, to give us the angle of incidence that we want to keep the aircraft nice and balanced. Yeah. And we do that by using what they call the variable incidence stabilizer. And the variable incidence stabilizer, we can move the whole thing. Yeah, we've still got the rudder there, so we've still got our flying controls, but all we're doing is adjusting the angle of incidence. The stabilizer is mounted to the fuselage. Yeah, so balance the nose down effect. Yeah, we could move the elevator up. Yeah, increases the drag, long-term nose tail heaviness. Rather than doing that, we can trim the angle of incidence, and that allows the elevator to remain streamlined with the stabilizer, so we've got full authority over the elevators. And away we go. Variable incidence stabilizer. Yeah, and it's just to counteract that nose down tendency of the aircraft, and that's caused by the center of gravity, center of lift couple. Yeah. Again, it's just showing the by moving the angle of incidence, yeah, we can keep the elevators fed. By keep the elevators fed, we're still generating the same amount of lift, but we're reducing the amount of drag that's needed. And the same in the opposite direction. Yeah, we could put the elevator up, but by moving the whole angle of incidence, yeah, we can keep the elevators fed, and we're again generating the same amount of lift on the tailplane. It does say stabilizers not normally adjustable on large propeller-driven aircraft because the airspeeds aren't high enough for that elevator drag to be significant. Jet transport aircraft, as I said before, we'd need extra power to overcome that drag. That's going to increase fuel consumption. Fuel costs money. Companies don't like spending money if they don't have to. So hence the variable incidence stabilizer. So I'm just reading through the notes as I'm going through to make sure that I'm not missing anything for you guys. And I'm not. Yeah. Other type of tailplane that we might come across. The only ones, admittedly, that I've come across in my career were in the military, hence the military photograph. But you may well come across what they call the slab tailplane. And the slab tailplane is just an all-moving tailplane. There's no control surface on the back. There's no tabs on it. Yeah, it's just one chunk of metal that moves up and down and acts as a great big elevator. Yaw control. Yaw is controlled by the rudder, and it gives us directional movement around the normal axis. Normal axis, sometimes referred to as the vertical axis. Yeah. Again, the rudder as far away as we possibly can get from the CG, hinged at the back of the vertical stabilizer. Yeah. moving the pedals left or right will move the rudder left or right. Yep, and again, it's acting as a control surface in as much as it's causing a camber on the wing. We're going to get positive pressure one side, negative pressure the other side, and that is going to move the aircraft left or right. Operated from the rudder pedals. Yeah, that's going to give us our directional movement. Yeah, sits nice and fair normally. Move left, move right. Yeah, it's going to cause the tail to move, which is going to cause the aircraft to yaw in the opposite direction. So if I push the right pedal down, yeah, the right pedal, the rudder is going to move this way, move to the right. The tailplane is going to get pushed to the left, which is going to cause the nose of the aircraft to move the right. Hence our instinctive movement yet again. Moving the rudder can cause the aircraft to roll. So as I move the rudder to the right, yeah, the fin is moving the aircraft to the left. As that fin moves to the left, the airflow hitting it is going to try to cause the aircraft to roll over, and that's known as an induced roll. So when we're manoeuvring the aircraft, we will generally move the rudder and the ailerons at the same time to negate that effect. So in addition to producing a yaw in straight and level flight, the rudder may also produce a rolling moment. Move the rudder to the right causes the wing to the left wing to move forward faster than the right wing, and because that increased speed, increased lift, yeah, the aircraft's going to start to roll. Hopefully you can see that we've moved the rudder to the right. The fin is moving this way, moving to the left. Yeah, as the fin moves to the left, it's causing the left-hand wing to accelerate. As that wing's accelerating, it's generating lift. Because it's generating lift, it's giving that rolling movement. Yeah. It does say, and again, it's more in the aerodynamics side. As that happens, the rudder extends above the aircraft's centre of gravity. So as well as causing that roll, yeah, because the rudder above the centre of gravity, we can get a twisting moment, and that twisting moment can cause a banking effect as well. Yeah, so with that, yeah, we're going to move the ailerons and the rudder at the same time normally, yeah, to keep the aircraft stable. I don't want to go too far back into aerodynamics, but there we have it. Yeah, as the aircraft starts to roll, that area of the fin is presented to the airflow. So as it's presented to the airflow, again the fin's being pushed around. So we're going to get that twisting moment in the aircraft. Yeah. Mentions spin. Yeah, it says that the moving the rudder to the right not only pulls the tail to the left, the nose to the right, but it may also spin the aircraft. Slip. Yeah, when we maneuver the rudder. Yeah, because that downgoing wing starts to move faster. Yeah, the upgoing wing producing more drag. The aircraft can start to slip down. So again, to prevent that slip, we need to pull back on the stick to adjust the angles of attack. That's more all of our aerodynamics, but moving the rudder, as we say, can have that adverse effects. Yeah. roll, as I said, that's the bit to remember at the bottom top of page 19. Roll normally collected by interconnecting the rudder and the ailerons. So when the rudder's applied, the ailerons operate, and that keeps everything nice and steady. Large aircraft, large transport aircraft at low takeoff and landing speeds, and we need large rudder movements to control the yaw. At higher air speeds, the rudder becomes less effective, and if we try to move the rudder, a big large lump of metal, into the airflow at high speeds, that could create large structural stresses. So what we do on your larger aircraft is we put in a rudder limiting system. So the highest speeds that we're going to fly at, we're going to reduce the amount of travel that we're giving to the rudder. We're still going to get that same yawing moment, but without huge back and forth movements of the rudder, and it's there to protect the aircraft structure. And yaw damping. Again, we're back into aerodynamics, but aircraft have a tendency to start a rolling yawing oscillation. That's known as Dutch roll. Your Dutch roll, the severity varies with different aeroplanes, but what happens with the Dutch roll, if we get a gust of wind, the gust of wind lifts a wing, as that wing lifts, the other one drops. As that wing drops, the tail of the aeroplane is hit by the airflow. The airflow will try to push the tail back round. That will push this wing down. This wing will start to rise. That wing accelerates. As it accelerates, it gets more drag, so it starts to drop. Because that wing's dropping, this one rises. Because this one rises, the airflow strikes the fin, pushes the fin round. This wing starts to drop. This wing starts to rise. And we go into this Dutch roll. And the Dutch roll, the aircraft is crabbing its way through the air, and it is horrible. The way we can reduce or hopefully eliminate the onset of Dutch roll is by using a yaw damping mechanism. So with the yaw damping, it's an automatic system, and as the aircraft senses it's going into a Dutch roll, as it senses there's a gust of wind hit the wingtip, started lifting it, what it's going to do is just flick the rudder, and by flicking the rudder, that's going to prevent the onset of that Dutch roll. It's just going to stabilize the aircraft. Yaw damping automatically moves the rudder approximately 3 degrees either side of neutral. And it's just a little flick of the rudder at 3 degrees either side of neutral, and it damps out the effects of Dutch roll creeping in. It's got its own its own built-in system. It's got its own little indicator switched on by the pilot before we go into flight. So what it does, just by moving the neutral, as the aircraft tips out, as the aircraft starts to move, flicking the rudder is just gonna bring it back to its neutral position. Right, just what the control surfaces do. I think that's probably a good time to grab a cup of tea then at the end of that. Just what the effects of the control surfaces are, what the control's doing. Hopefully we should know all that. Second nature, we work on aircraft. So what we'll do, we'll have 20 minutes there. We'll go and have a cup of tea, and then we'll come back and look at some of the other control arrangements that we might find on our aircraft. Anybody got any questions before we do that? No, no questions. Right, I'll see you in 20 minutes then.
Okay, Jim. Thank you.
Right, guys, got everybody back? Deathly silence, I'll assume so. So we'll kick on with the next bit then. And the next sort of control setup that we might come across is an aircraft fitted with canards. Yeah, and the canard is where the horizontal stabilizer is in front of the wing. Yeah. So rather than having a conventional tailplane, the horizontal stabilizer at the front of the aeroplane, at the front of the wing. Canard may also be known as the foreplane or a forward wing. It says if a foreplane provides less than 1/4 of the total aircraft lift, it's considered to be a canard. That's kind of the official thing, but most people, a canard is just if a wing in front of the aeroplane. Yeah. Normal aircraft, the lift acts behind the center of gravity. We're going to put a download on the tailplane for the aircraft. So the wing has got to produce extra lift for the compensate for the tailplane download, slight increase in drag. When we use a foreplane, the foreplane, the lift that's being generated is added to the lift of the wing, so they're not fighting against each other, but if you like. So if we use a foreplane to balance the aircraft, lift added to that of the wing, so the wing can be smaller. Same total lift of the tailplane increases drag, foreplane reduces drag. Increased area of the lifting surfaces allows a smaller wing. Longitudinal control and trim provided by elevators hinged to the trailing edge of the foreplane. And when the wing flaps are lowered, the nose down turning effect again is balanced by the foreplane. So the canard is quite a useful bit of kit. The foreplane. Canard is pitched nosed up. The wing lift increases, produces a nose down turning moment, and that in turn lowers the nose. So we can get control from this thing as well. We can have elevators on it. Conventional wing behind, but the wing is a lot smaller. And this particular setup, we've even put a fin with a tailplane on. So the foreplane, the canard there, helping with the lift. The fact that we've got that, we can get a lot more cabin room because the wing, because we've got lift generated at the front of the aeroplane, we've got the wing at the rear, smaller wing. We can now make a lot more use of the available fuselage space and put the wing spars through the fuselage at the aft of the cabin. We can put the thrust at the aft of the cabin as well. So quite a nice little arrangement. The foreplane is mounted at a larger angle of attack, angle of incidence, I apologise, than the main plane. So because we've done that, if the aircraft gets to the point of stall, the foreplane is going to stall before the wing. Because the foreplane stalls first, the nose of the aircraft going to drop. There's going to be more lift generated on the wings, which is going to bring the aircraft back from the stall point, from the stall angle. So foreplane, page 22, foreplane mounted at a larger angle of incidence than the main plane. So whack a highlighter through that, just so we know. Make sure that the foreplane stalls before the main plane, so the aircraft won't stall or spin. Very, very difficult to stall one of these aeroplanes. Because the foreplane's stalling, the nose is going to drop, and that prevents full stall of the aeroplane. Best place for the main plane on a conventional aircraft through the fuselage behind the cabin. So it said that would require a larger tailplane to balance the lift. So aircraft is a rear-mounted tailplane balanced with a small foreplane, sharing the lift with the main plane. Tailplane elevator return for pitch control. We can make a lot more use of the cabin space. So you got your foreplane. That's quite a nice picture of it. You can see we've got the elevators fitted to the foreplane. We've got wings at the back of the cabin, so we're making as much possible room use of space, little ailerons just to give us our roll control, engine at the back. Away we go. What we're saying with our canard arrangement, 4-plane arrangement, yeah, smaller types, better use made of the fuselage space. Larger canards, the main plane can be located at the rear, giving an uninterrupted full-depth cabin. We've already mentioned that. Rear fuselage mounted propellers or wing mounted push propellers, the noise is behind the cabin, so it makes it a lot quieter, more comfortable. Wing mounted push propellers, the wing's clear of the propeller slipstream, and that allows the laminar flow over the wing, and it says reduces the drag that the aircraft's going to suffer. So they do have a few advantages, the canard arrangement. Canards or 4-planes. The only thing that really need to mention in that lot is the fact that the 4-plane is mounted at a higher angle of incidence than the main plane. Makes it just about impossible to stall the aeroplane. Elevons, yeah, delta wing aircraft. What we're going? Hello.
Hello, Jim.
Hello.
In canard aeroplane,
Yeah.
as the elevators are attached to the canard surface, so
Yes.
so just like it will be opposite to the normal, the elevator movement for longitudinal control will be opposite to the normal design. Just like in normal design, if the elevator goes down, then the tail goes up and the nose goes down. But here in the canard, if the elevator goes down, then the nose goes up and tail goes down.
Yeah.
So it will be, the movement will be opposite. Elevator movement will be opposite of normal. I think this should be the movement of elevator in the canard should be opposite of the
yes, but
normal for longitudinal.
You're right in what you say, but none of that control movement is mentioned in the notes. So don't start weighing yourself down with things moving in opposite directions. Yeah, don't. As I say, you're right in what you're saying. Yeah, that's fine, but don't overcomplicate your thinking.
Okay, we should just focus on the notes.
Yes, yeah.
Okay, Jim. Okay, no problem.
Yeah.
But
actually,
yes,
you are right. Yeah, if I put the elevators down on the 4-plane, yeah, I'm going to pull back on the stick. The elevators are going to go down, and that's going to lift the nose up. So I'm still getting that instinctive control. Yeah, but just as you say, on the if I pull the stick back on the conventional aircraft, the elevators would go up, which would push the tail down, which would pull the nose in the upward direction. Yes.
Okay, Jim. Okay.
Yeah. All I'm saying is, just be careful you don't overcomplicate things. Yeah.
Okay, Jim. Okay.
But yes, you are correct. With the elevons and rudivators, yeah, they are combined controls. So delta wing aircraft, yeah, they've only got the trailing edge for the controls, and you're limited in your space on the trailing edge. So what we've got is the control surface on the trailing edge of your delta wing acts as the aileron and the elevator. So it's called an elevon. Yeah, it's a mixture of aileron and elevator. If I move the control column backwards or forwards, yeah, the control surfaces will act together as elevators, and they will give me my pitching control. If I move the stick left or right, they will act differentially and give me the roll control. Yeah, so that's the setup of the elevons. Yeah, so turn left or right. Yeah, one set will move up, the others will move down. Act as ailerons. Move the stick forward or backwards. They'll move up or down. Act as elevators. Yeah, control systems interconnected so that the elevons can move to produce pitching and rolling movements at the same time. So if the aircraft was in the climb, for example, and I wanted to roll the aeroplane, yeah, what I'd do is I'd have my stick pulled back, yeah, which would put the elevons up, which is pushing the tail of the aeroplane down, bringing the nose up. Yeah, so as I'm climbing, if I wanted to roll, I'd move the stick to, let's say the stick to the left. Yeah, the right-hand elevons would go down slightly. Yeah, which again would create more lift. Yeah, you get more drag on the left wing, more lift on the right wing, which would cause the aircraft to roll in the required direction. Yeah, so yeah, the combined control surface, they'll act in two manners. They'll act as elevators and they will act as ailerons. Yeah. If I want to maneuver the aircraft, depending on which direction I'm going, yeah, if the elevons are up, then one side or the other would go down to give me that aileron effect. So I could have a pitching and rolling motion at the same time. Ruddervators, yeah, again, they're a combination type flying control, but they're a combination of the rudder and the elevator. Yeah, the ruddervator is sometimes known as the V-tail or the butterfly tail. So if you can imagine that was a horizontal tail plane, you'd have your elevators going up and down conventionally. If that tail was straight up, you'd have your rudder going left and right. So all we're doing with this is combining the two, so we get the rudder function and the elevator function, yeah, known as ruddervators. Ruddervators moved up or down together using the control column to provide pitching control, or opposite to each other by the rudder pedals to give us yaw control. Yeah. Normally, if I was in class now, I'd grab a couple of books and I'd show you how the things are working. I will try and do it on the camera. Can you see me at the minute?
Yes, Jim.
Brilliant. Right. Imagine that as a fin. My hands are the rudders. Yeah, the rudders would go left and right, give me directional control. Imagine elevators. Elevators go up and down, giving me pitching control. So what I'm going to do now is move the rudder out the way and the elevator up the way. So moving together, I'll get rudder control. Moving the other way, I'm getting elevator control. And if I try to do it, and normally I've got a book in my hand to do that with. If I try and do it now, I'm going to fracture my wrist. Yeah, but hopefully you get the idea. Yeah, the picture on the book. Yeah, try it yourself. Yeah, put your hands up as if you have got a rudder. Move the rudder left to right. Yeah, try it as a elevator. Move the elevator up or down, and then double them up. So you've got a twin tail, rudder, elevator, yeah, and then split them up, and that gives you an idea of how they're moving. But the only thing that we really need to worry about is the fact that it's a combination of rudder and elevator. Yeah, and there you can see the control surfaces on the back of the stabilizer. It works. It's an arrangement that works. Yeah, smaller aircraft, and you do see the V-tail aircraft flying around now. Yeah, it says used on light aircraft. Generally, it's rarely used. There are aircraft around with it. Yeah, it says the advantage of the V-tail: less weight and drag due to the smaller number of control surfaces. Right, high lift then. Yeah, high lift devices. Yeah, aircraft in the cruise. Yeah, it's fine. It's flying along. Lift equals weight. Thrust equals drag. Everything in balance. But now we need to get that aircraft onto the ground. Yeah, we need to get it up into the air. So to give us that assistance, we're going to fit high lift devices to the aircraft. High lift devices are going to change the shape of the wing, and in some cases change the size of the wing. Yeah, the high lift device, as the name suggests, is going to generate a lot more lift, so we can fly the aircraft at much slower speeds. So when we're coming into land, we can slow the aircraft right down. We can have a much steeper approach path. By doing that, we can get the aircraft down quicker, clear the runway. We can get more aircraft coming in, and that makes things more economically viable as well. So high lift devices split into two groups. We have the trailing edge devices and the leading edge devices. Yeah, your leading edge high lift devices again are subdivided into two types. We either have leading edge flaps or we have slats, and then your trailing edge, we've got trailing edge flaps. Yeah, as it says, the retracted, the part of the aerofoil shape of the wing, everything happy. When they extend, they change the camber of the wing to increase the lift that we're generating. One to note on page 26 there, propeller-driven aircraft don't normally have leading edge devices. They don't normally have those because the slipstream from the propeller keeps the airflow over the wing flowing nicely, keeps the boundary layer jogging on. So our leading edge devices then, as we say, the two groups, leading edge slats or leading edge flaps. The difference is that slats have slots. Yeah, the idea of the slat is, hopefully you can see it on the screen there, as the slat extends, it's forming a slot between the slat and the aerofoil. Yeah, and by extending the slat and creating that slot, the air flows through, and it carries the boundary layer along, re-energizes it, and keeps it attached for longer. Yeah, so long as it's attached, it's generating that lift. Once the slat's retracted, forms part of the leading edge of the wing, and away we go. The other difference, just seeing if I can see it. Don't worry about the increases in angle of attack. Obviously, we're generating more lift, so we can increase the stall angle of the aeroplane. Decreases the aircraft's stalling speed because we're generating that lift. because you're pushing air across the top of the wing, you're reducing the span-wise flow of air that's coming through, which is fine, which again is helping the aircraft. The other thing I was thinking of, difference between leading edge flaps and slats. The slats have slots. The slats also have an additional position. They are either fully retracted, a mid position that we use for takeoff, or extended that we use for generally for landing. Yeah. Once they're extended, as we say, that flow across the wing is greatly increased. It will hugely increase the lift of the wing. So now, because we've increased that lift, we can fly at much slower speeds, higher angles of attack, and we're not going to stall the aeroplane. But yeah, that's slats from the notes. Other aircraft, some aircraft have automatic slats. The automatic slats, there's no cabin control from or flight deck control. They're used on smaller aircraft, and they're just allowed to extend by the pressure of air acting on them. So the faster the aircraft's going, the airflow will push the slat in. It'll form part of the leading edge. Slow the aircraft goes, or if the aircraft starts to approach the stall angle, the slats will automatically deploy. They'll drop out and again increase that lift for us. Other aircraft have just permanent slots as part of the leading edge assembly. And again, that has exactly the same effect. As the aircraft slows down, airflow goes through the slots, energizes the boundary layer. So there are different types of slat that we might come across. Leading edge flaps do not create a slot. All the leading edge flap does is at lower speeds, we put the flap down and it increases the camber of the leading edge. Because we're increasing the camber, we're again generating more lift at lower speeds. So the leading edge flap just changes the camber of the wing, which changes the effective chord line, if you like. Hopefully this will work. Your chord line from the leading edge to the trailing edge against the relative airflow. Giving you your angle of attack. As I drop lower the flap, I'm extending the chord line. I'm extending the camber of the wing and extending the camber of the wing. I'm giving myself, I'm reducing the angle of attack, so I'm giving myself more to play with. So as the angle of attack increases, nearer I'm getting to the stall. If I drop that slat, I've got more angle of attack available to me. So I'm less like increasing the lift. I'm not going to stall the wing. Or I've got more to play with before I stall the wing. Just a little screw jack that they operate on, and the lower just to droop the leading edge. Other types of leading edge flaps, we get Kruger flaps and variable camber leading edges. Kruger flaps form part of the lower surface of the skin, the lower skin of the wing when they're retracted, and then as they extend, as you saw before, they're changing the camber of the wing. So the Kruger will drop straight out. The variable camber is a type of Kruger flap, but as it's extending, the nose of the flap extends out as well. So as you can see from the picture, it's all nicely tucked up. As we extend, the nose is changing its angle, so it's changing the camber of the wing during its extension process. variable camber. Yeah, all tucked up. Yeah, extends out. Yeah, and then your variable camber one, the folding nose one, again all tucked up, but adjusting the camber even more as it extends out. Krugers used in so different areas. They're used where we can't get the slat to run down the full length of the wing, and deep sections of the wing. It's a lot easier to manufacturing and design to use Krugers than it is to use slats or flaps. Yeah, so again, good example there. You can see the slots being formed. The inboard side, yeah, you can see we've got the Kruger flap with the camber on the leading edge there. So a bit of a combination there with the slats and the Kruger flaps on the inboard side. The trailing edge flaps then, as the name suggests, fitted on the trailing edge of the wing. Because we're fitted on the trailing edge of the wing, we're changing the camber of the aerofoil as those flaps drop down. Some flaps, the extension flaps, we can actually change the surface area of the wing as well. And if you think back to your lift formula, yeah, go on then. What was the lift formula? Anyone?
Half rho V's and no, sorry. Yeah, I got confused.
Yeah, you were going right. Lift equals what? V
Half
squared?
half rho with the
Yeah.
Half rho.
coefficient of lift.
Yeah. S is your surface area. So that's what we're talking about. With some types of flap that we'll see in a minute, we can increase the surface area of the wing. So if I increase the surface area, I'm going to increase the lift available to me. If I increase that lift available to me, I can reduce the speed. Yeah, so as I reduce speed, increase the surface area, yeah, I can either increase or maintain the lift that's available. Yeah, again, altering your coefficient of lift, which is your angle of attack, by altering the various components in the lift formula. Yeah, I can fly at relatively low speed for a lot of lift, which is a good thing. So you drooped flaps, yes, I've been through that. Krugers, yeah, we mentioned all those. Nothing there that we need to think about. Variable camber, yeah. Yeah, so changing the wing, the wing camber then with our trailing edge flaps. There are different types of flap. There is the plane flap, and the plane flap, as the name suggests, is just a flap that we lower down, yeah, and that is going to change the camber of the wing. Yeah, plane flap. It says sometimes referred to as the camber flap. I can't say I've ever heard that one, but it's apart from in the notes. But it's just lowered. Rear section of the wing hinges down, increases the camber, and again generates that lift for us. Normally found on smaller aircraft types, the plane flap. The slotted flap, yeah, has the same effect. It's changing the camber of the wing, but as it lowers down, it creates a slot between the lower edge of the wing and the flap itself. So again, by creating that slot, we're having a similar effect to that we had on the slats. We're generating an airflow over the top of the flap. By generating that airflow, we're keeping the boundary layer energized and keeping it attached for longer. So we're increasing the lift. Again, your slotted flap tends to be on the smaller aircraft types. Split flap, yeah. When the flap is retracted, it forms the lower surface of the wing. When we extend it, basically, it's just the bottom skin of the wing dropping down again to form that camber. Flaps lowered, the air flowing below the wing, forced to change direction, which is exactly the same as having a camber on the top of the wing, and that is again gonna generate the lift that we require. So we're changing the camber of the wing on the bottom, increasing the pressure, yeah, which is again generating that lift for us. Yeah, not a lot else to say there. The extension flap, or the Fowler flap as it's frequently known, it lives under the trailing edge of the wing, yeah. And as we extend the flap, not only is it drooping down, it's also moving out the way as well. So it's a combination where it's increasing the camber of the wing, but it's increasing the surface area of the wing as well. Yeah, the extension flap, because we're increasing that camber, because we're increasing the surface area, that generates an awful lot more lift. Yeah, it's really rather good. So when we're in the cruise, yeah, it'll sit stowed. It'll form part of the aileron shape. When we go to take off, yeah, we're just going to lower part of the flap just to give us a small amount of lift. So as speed increases, yeah, that lift's going to increase. We're going to generate sufficient lift to overcome the weight, and then we can retract the flap. When we come into land, we want to slow the aircraft right down, so we need to increase the lift available. So as we extend the flap, it's increasing the camber, but it's also increasing that surface area. We can further increase the efficiency of that flap by introducing a vane at the front of it. By putting that vane on, it creates a slot, yeah, and by creating that slot, again, we're energizing the boundary layer, and in the front of the vane, there's a slot as well. So again, that's even increasing that boundary layer energy even more. So it keeps the air attached for a lot longer. So again, we're increasing the lift nearly twofold. It says we can increase it as much as 90%. Big disadvantage of the extension flap, and again worth a highlight at page 35. Disadvantage of that is that there's a large rearward movement of the centre of pressure when the flap's lowered, and that will give a nose down pitching moment to the aircraft. Yeah, so the flaps have got to be introduced slowly into the airflow, and as we introduce the flaps, then the elevators will adjust normally automatically to compensate for that pitching movement. Again, just an example of your flaps. The propeller aircraft, no leading edge devices because we've got that slipstream, and generally that slipstream over a propeller aircraft is sufficient to keep the energy going over the flaps. So with your propeller aircraft, we've got an advantage there. If we add slats and flaps, yeah, the lift of the wing is really enhanced. And just a couple of examples on the slide, the different types. You can see your extension flaps there, yeah, and the sections of them. We've got the split flap here. Hopefully you can see the split flap, and the plain flap just as it says, just drops down. The Fowler flap, the extension flap, and this one a 3-section one. Just showing the big increase in the surface area of the wing that we can generate with our high lift devices. Yeah, just examples in the notes. Shows you some nice pictures there of what's going on, and shows you the coefficient of lift, the increase that we can get by the addition of those leading and trailing edge devices. High lift required for takeoff and landing in large transport jets, normally provided by the combined effect of the leading and trailing edge. Propeller aircraft don't normally use leading edge devices. Sufficient lift provided by the trailing edge flaps and the propeller slipstream over the top of the wing. For takeoff, flaps load to a small angle, gives extra lift, very little increase in drag, and don't forget on takeoff the velocity of the aircraft's increasing as well. So we're speeding up, so we don't need that huge amount of control surface for us. Leading edge slats, 2 extended positions, takeoff and landing, or the leading edge slat will either be retracted in takeoff or in the landing position. Takeoff, it's extended without forming a slot. Krugers and cambers either retracted or extended. Leading edge flaps are either extended or retracted. 39, page 39, an aircraft will always take off into wind, and it will also land into wind. Yeah, so bottom paragraph, for bottom 2 paragraphs on page 39, stick your highlighter through those. Aircraft will always take off into wind to get the flying speed in the shortest possible time. It'll land into wind so it can touch down with the lowest ground speed, and that means we can stop in a shorter distance. So please, page 39, just stick your highlighter through the takeoff and landing, always into wind.
Hello, Jim.
Yeah.
This in page 35, there is in last paragraph, this type of flap would increase lift by 100% on that part of the wing where the flap is fitted. It also causes a large rearward movement of the center of pressure. And what will that cause? Large rearward center of the pressure, nose down pitch. That will cause nose down pitch.
Yeah. So if just get me my little pen going. Yeah, there's your aeroplane. Yeah, the center of pressure behind the center of gravity. Yeah, if you put the flaps down, then that center of pressure is going to move backwards. Yeah, as it moves backwards, it's even further away from the center of gravity. So the aircraft is going to try to pitch nose down. You with me?
Okay.
So
Thank you.
That's your wing. Yeah. Let's say the center of pressure is there. Yeah. If I put the flaps down now, that center of pressure is going to move to round about here. So the center of pressure is going to move rearwards. Yeah. Now you're going to get that lift. It's going to try to cause the aircraft to pitch nose down.
Okay, Jim. Okay. Thank you, Jim.
Okay.
Okay.
आजकल गेम नहीं खेलती ना क्लास का टाइम यहाँ पर से हैरी पॉटर यूट्यूबर तो यार बनी
Anybody else? Anybody else? Yeah, just your examples of the different types of devices. Yeah, everything up in
Excuse
stored
me, Jim.
position, retracted. Yeah.
Would you please repeat the highlight in page 39? Would you please repeat the highlight sentences in page 39, which you have said? 39.
That was the
Landing and takeoff into the wind.
bottom at the bottom of the page about the landing into wind and taking off into wind.
Okay, thank you.
Okay. Just the differences. Yeah, everything retracted. You've got your nice aileron aerofoil shape. Yeah, when we go to take off, yeah, we're going to extend slightly the flaps, and the slats will go to takeoff position, and then landing. Yeah, your extension flaps will come out even more, create those slots, and that will keep your boundary layer going. That will give you all that extra lift. Yeah, we can put on additional bits. We could put on an aft flap, a mid flap, and a fore flap, or the vane, the flap, and the auxiliary flap, as it calls it on this picture. It's creating the exact same effect, but between the mid flap, the aft flap, or the auxiliary flap, again, there's a slot being formed. So even though this has hugely increased the camber of the wing, yeah, we're still getting the airflow over it to give us that additional lift. Triple slotted flaps, again, just building up on what we've already said. Won't go too deep into it, but just shows the increase in angle of attack, the increase in coefficient of lift that we can get by using these devices. And the graph just shows the different effects for the different types of high lift device that we've got fitted. Yeah. We said that from your propeller aeroplanes, yeah, we've got all that slipstream over the top of the wing, so we don't really need to use leading edge devices. Yeah, there's sufficient flow, but we could use slotted flaps on the trailing edge if the aircraft design demands it. Yeah. Yeah. One of the problems that we could get with our flaps, though, is what they call flap asymmetry. And that is where the flaps do not extend symmetrically. They don't come down together. If that happened, yeah, and if it happened in flight, we would get an awful unrecoverable rolling moment of the aircraft. So what we do is build in an asymmetry protection, whereby if the flaps get to a certain point where they're mismatched, I think it's 5 degrees mismatched between the left hand and the right hand side, the system will lock up, yeah, so that they won't travel anymore. So you asymmetry protection, yeah, stops the movement of the high lift devices if the angular difference between them exceeds, it says a predetermined limit. I think it's about 5 degree difference between them. Load relief, yeah, if we lower the flaps at too high an airspeed, obviously airflow is going to create structural damage. So the load relief, again, we'll look at it when we do the flying controls, but that just if we lower them at too high an airspeed, they will retract until the airspeed is reduced to a suitable value. It's sometimes called blowback, yeah, but the flaps just go, if we're at too high an airspeed, the flaps will retract slightly till the aircraft is slowed down, and then they'll come back to the selected position. Indications in the cabin, and it'll tell you the position of the flaps, and if you've got them, the position of the leading edge devices. Flaperons, yeah, some large transport aircraft, the 2 sets of ailerons on each wing. We're going to look in more detail at those in a bit, but the low-speed ailerons mounted near the wingtip, the all-speed ailerons on the inboard portion of the wing. So that kind of reduces the amount of space that we've got to fit flaps. Yeah. So one of the ways that they overcome that is to have one of the control surfaces acting as both flaps and ailerons, duplicated. Yeah. So with the flaperons, they can lower together, act as flaps, or they can operate differentially to act as ailerons. So if you remember before, we saw elevons on the delta wing aircraft doubling up as control surfaces. The flaperons do the same. Yeah, the flaperons will act differentially as ailerons, but they will also lower together and act as flaps. And the reason for that is we've got 2 sets of ailerons on our larger aircraft. The reason for that we will come on to later. All right, I'm at that 11:20. We'll just have a 10-minute break there. Yeah, been going for a while. We'll just have 10 minutes, and then we'll wrap off up to lunchtime. Before I do, has anybody got any questions? No. Okay. Right. 10 minutes then.
Mr. Jim,
Yeah.
flappy rule is to reduce the asymmetry, yeah?
Yeah. I'll tell you what. I'll go back over it after we've had a quick break because my eyes are hurting.
Okay.
All right. Right then, somebody asked me just to go over asymmetry again, flap asymmetry. When the flaps operate, obviously they're operating in conjunction with each other. So the flaps on the left-hand wing, the flaps at the right-hand wing are going to go up and down together at the same time by the same amount. That way, we're generating an even amount of lift across the whole wingspan. There is always a possibility, though, that the flaps could fail for some reason on one side, and one side would carry on travelling down, and the other side would remain in its selected position. Yeah, either up or it'll jam part way, and the other side will carry on. So you end up, as you see on the slide, you could end up in the situation where you've got the flaps extended on one side and retracted or partially retracted on the other. And that is what they call a flap asymmetry. If we allowed an asymmetry to I was going to say start, that's not the right word. If we allowed an asymmetry to continue, should we say, yeah, what would happen is that the flaps that are going down would be creating lift. The flaps that are jammed wouldn't. So the aircraft would enter a roll. And there is always a possibility that that roll would be unrecoverable. Yeah, because the flaps had travelled too far. We wouldn't be able to reselect them because you've got a jam on one side. So the aircraft would start rolling and we'd never get back. So the asymmetry protection system is monitoring the travel of the flaps. Yeah, as it's monitoring the travel of the flaps. If there is a discrepancy between the two of more than, it says in the notes, a predetermined limit, I've got it in the back of my head, I think it's about 5 degrees separation, the whole system will jam, it will lock up, yeah, and that way it prevents any uncommanded roll or unrecoverable roll of the aircraft. So the asymmetry protection system monitoring the travel of the both sets of flaps, and if there's a mismatch between the two, it will lock the system up. I can't remember who asked, but has that answered the question? Who asked me about asymmetry?
Yeah.
Pushpa, has that answered your question?
Yes. Yes. Okay.
You sure?
Yeah. Sure.
Okay, right. So that was our flap asymmetry. Yeah. The load relief. Yeah. If we load the flaps into the airflow at too high an airspeed, the airflow is going to try to push the flaps back. If we didn't allow it to do that, it could cause structural damage. So what happens with the load relief is that the airflow will push the flaps back up until the airspeed is reduced enough for the flaps to come down to the selected position. Again, the mechanical side of all this, we're going to look at, I think we start it tomorrow, finish it off on Monday. Yeah, so that's the mechanical side of things. Flap asymmetry. The flaperons, as I was trying to say earlier, the flaperons are a double whammy again, a bit like our elevons, but the flaperons are a combination of aileron and flap. Yeah. On a large aircraft, as we'll see later on, there's two sets of ailerons. There's the outboard ailerons, and then we have a set of ailerons inboard. but that means we run out of wing space, so we run out of space for the flaps. Yeah. So what they do instead is they will use a flapper-on, as we see there, and the flapper-on doubles up as an aileron. It assists the aileron, but when required, it will also droop down and act as a flap. So it'll increase the flap area as well as operating as an aileron to assist the ailerons. That is our flapper-on. If you think back, oh God, it's a couple of years now. The Malayan aircraft, Malaysian. I think it was Flight 370, but it got lost. It crashed. It vanished. And one of the first indications that they had that the aircraft had flown into the sea was a flapper-on was washed up on a beach. Right. Has anybody got any questions on anything there? We're a little bit ahead of the game at the minute, actually. So if anybody's got any questions, now is a good time to be asking.
Jim,
Yeah.
do you have to remember that all these lift for the different types of leading and trailing edge categories of these items? There's mention some each and everyone's lifting percentage.
How do you mean?
Do you have to remember that?
Well, if you have flaps and slats, you can get 120% more lift.
Yeah. This.
No.
Okay.
You need to know what the flaps do. You
Yeah.
need to know what the slats do. You need to know the difference between the leading edge flaps and the leading edge slats. You need to know the different types of trailing edge flap that we might come across. But and we need to know that they are there to give us more lift at lower speeds. But the actual percentages of lift, no.
Okay. Okay. Thank you, Jim.
Okay.
Okay.
Anybody else got any questions at all? Right. The next control surfaces then that we need to have a look at are spoilers. Well, they're called drag-inducing devices. Yeah, and the drag-inducing devices are generally accepted as spoilers. Spoilers are frequently referred to as speed brakes. Yeah. It's a bit of a misnomer because the spoilers fulfill different functions. Yeah. They will act as a drag-inducing device both in the air and on the ground. As it says in the notes, the flat panels and they're hinged at the forward edge. When the spoilers are deployed, they will rise up and they will reduce lift and increase the drag on the aeroplane. While we're in the air, that allows a controlled descent. Yeah, it's going to limit the airspeed. So as the aircraft's coming down, putting the spoilers up is going to slow us down. Slow us down so we can descend without speeding up. Yeah. So the spoilers in flight are generally referred to as speed brakes because they're slowing us down. The flight spoilers, I should say that the spoilers are split into two groups. Yeah, we have flight spoilers and we have ground spoilers. The ground spoilers do as their name suggests, they will only operate on the ground. The ground spoilers trash all the lift on the wing. So once the aircraft's landed, the ground spoilers will deploy right the way up, and any lift that might be on the wing is totally ruined by the ground spoilers. The flight spoilers will act in the air and on the ground. Yeah, so we get two shots with the flight spoilers. Flight spoilers, as I say, if we're descending, we can select them up. They will stick up in the airflow. They'll reduce the lift. They will increase the drag, and they will allow us to descend without accelerating. Yeah, the flight spoilers also operate differentially, and they are there to assist the ailerons. And in some cases, we can use a spoiler instead of an aileron. Yeah. So as the spoiler lifts up in its roll method, one side will lift, the other side will stay flush with the top of the wing. The upgoing spoiler is going to create drag. It creates drag on the wing. The lift is going to reduce so that wing will start to drop. The opposite wing, because it hasn't got that drag, will start to rise, and that will give us our turning effect. So we can use the spoilers in a roll control. We can use them simultaneously to slow the aircraft down. And then the flight spoilers as well, once we are on the ground, yeah, once the wows have made, the flight spoilers will deploy to their full extent on both sides of the wing. So it makes sure that the full weight of the aircraft is down on the ground. Because you've got the full weight of the aircraft down on the ground, the brakes are a lot more efficient. Yeah, we can steer the aeroplane. And one of the other things it helps is to prevent aquaplaning. So if you've got a really wet runway, yeah, rather than having the aircraft skipping along the top, the full weight of the aircraft will go onto the wheels. So trashing all that lift can help to prevent aquaplaning as well. Somebody dinging? No, everybody in. Lovely. Yeah. So you roll spoilers, yeah, acting as assistants to the ailerons. We can use them as speed brakes to slow the aircraft down in the ground. The ground spoilers are there purely for use on the ground to spoil the lift over the top of the wing. Yeah. Like I say, flat panels, normally located in front of the ailerons because we're using to assist the ailerons. Two groups, ground spoilers and flight spoilers, and they are just flat panels, normally lie flush with the top of the wing. When they're deployed, they will protrude up. Just like that. Yeah, your ground spoilers and your flight spoilers. I really must take out these copyrighted photos before I get sued. Yeah. Anything else I need to say there? No. Spoilers may be fitted to both jet transport aircraft and propeller-driven aircraft types. So again, just showing the panels, the distribution of them, and as we saw from the picture, how they're mounted on the aircraft. All right, using those spoilers for roll control, They're going to be there to assist the ailerons. Yeah. In your large aircraft, your high-speed aircraft, we might not need to move the ailerons at all, but by operating the spoilers and just creating that little bit of drag on the wing, yeah, we can get roll control. So the roll spoilers, yeah, the spoilers operate differentially, yeah, by movement of the control wheel. That's your control wheel, control column. As we move that left and right, the spoilers are going to move differentially. So your upgoing aileron, yeah, will move up, and the spoilers will move up as well. The movement of the spoiler, how much spoiler you're going to get, is directly proportional to the input on the control wheel. If we want a huge amount, yeah, the wheel's going to be moved right over. The spoiler is going to come even further up. Yeah, if we only need a slight amount of movement, the aileron will rise slightly, the spoilers will rise slightly. Yeah, so spoilers operate differentially when the control wheel's rotated. During a roll, the surfaces move in proportion to the aileron movement. Spoilers on the downgoing wing move upwards, decreases the lift on the wing, increases the rate of roll of the aircraft. Spoilers on the upgoing wing remain flush, and the aileron itself will generate the lift that we're after. Everybody okay with that? Any problem there? Using the spoilers as speed brakes, the idea is we're going to slow the aircraft down in flight. So when they're acting as speed brakes, the spoilers on each wing will raise together by a selected amount. Yeah, and the amount they're raised is determined by the pilot, and the pilot uses the speed brake lever in the cockpit. Yeah, it's normally mounted on the throttle side of the throttle quadrant. Yeah, and he will within the range of the flight detent. Yeah, he's able to select how much spoiler movement he wants. Some spoilers you get automatic range of movement. Yeah, kind of depends. But in this case, yeah, we're going to the flight detent, and the spoilers will extend to a predetermined level. Right, let's see where we're going from that. Yeah, spoilers operated by the spoiler lever, as we said. If they're acting as speed brakes, yeah. If the speed brake lever is in the down position, all the spoilers are nice and flush with the wing. Yeah, fully retracted, and each of the positions on the selector has a little detent. When we talk about detent, it's just a method of holding it in the correct position so it doesn't get moved accidentally. It's got to be a positive movement of the lever. Yeah. As we move that lever back away from its down position, yeah, the spoilers are signaled to rise. Yeah. As we pull back, the spoilers are rising, proportional to what the pilot wants. Yeah, and when they reach the maximum angle required for flight, yeah, the lever's at its flight detent position. So flying along quite happy. Yeah, I want to slow down. I'll move the speed brake lever from the down position. I'll pull it back through, and as I'm pulling it back through, the spoilers are lifting up into the airflow. Once we're at the maximum selected position, we'll be at the flight detent. During flight, yeah, we can, if necessary, have speed brake and roll commands occurring together. Yeah, that is achieved by what they call the mixer unit or the mixer box. She'll come on to that in just a second. Yeah, just while the slide's still there, the slide's still up. Yeah, I've gone to the flight day temp position. I'm pulling the aircraft back. If I need to make a roll input, yeah, then whichever way I'm turning, yeah, if I want to turn to let's say this direction, the spoilers on this wing will retract slightly, yeah, which means I'm going to get more lift on one wing than I am on the other, and that's going to introduce my roll input into the aircraft. Once I've finished rolling, yeah, and I come back to the straight and level, and the spoilers will pop out to their original position so that they're all nicely lined up. Slow down, slow down, slow down, and then once the aircraft is on the ground spoilers will deploy. So now I'm putting all the weight of the aircraft onto the wheels because I'm ruining the lift over the whole wing surface. Yeah. Ta-da! Anything else I need to say there? No. Nice little picture of what I'm trying to say on page 46. Yeah, so spoilers partially raised, fully raised when the wing's going to drop, partially raised. Again, with that aileron assistance, we're going to generate the lift. So we're going to be able to turn the aircraft. We're going to get a roll command in there, maneuver the aircraft to where we want it to be. Spoilers used as speed brakes. They can normally be used at any airspeed, but at higher airspeeds, obviously, we're putting this great panel up into the airflow. The higher the airspeeds are, the more the spoilers are forced down towards the wing by the airflow on them. As they're protruding, though, they're going to start to slow the aircraft down, and as this aircraft slows, then they're going to start to creep out again as they're having that slowing effect on the aeroplane. Coming into land, yeah. What will happen as I'm coming into land, the pilot will put the selector lever into the armed position. Yeah, and the armed position is getting everything ready for the spoilers to deploy to their full extent when the aircraft touches down. Yeah, so flight spoilers and the ground spoilers on both wings are going to automatically rise to their maximum angle on touchdown. There must be certain conditions to be met before that can happen in the auto mode. Those 4 bullet points on page 46 you'll need to know about. There are 4 conditions for the ground spoilers to fully deploy. The speed brake lever has got to be in the armed position. Yeah, the weight of the aircraft has got to be on the ground, and that's through the WOW switches. So the WOW switches are going to send a signal up to the spoiler controller to say, yeah, we're now on the ground. The throttle levers or the thrust levers need to be in the idle position, and the wheels need to be rotating. Yeah. For those conditions to be met, what happens is we're in the armed position. The aircraft lands. The weight of the aircraft goes onto the WOW switches. The pilot has got the thrust levers back at idle. The wheels are still turning. Yeah. Once that's happened, then there's a little actuator inside the throttle box that will drive the speed brake lever from armed to fully up. and that will deploy all of the spoilers to the fully up position and trash all of the lift over the wing. So now the full weight of the aircraft is on the ground. The braking is a lot more efficient because we're in contact with the tarmac. That's going to give me directional control, steering, and it's also going to reduce the chances of aquaplaning on our aircraft. Yeah, so that's your lift dump when you land, and the 4 criteria that we've got to meet. Spoilers fully raise up. Yeah, the wing lift's reduced. Aerodynamic drag, it says more than doubles. Yeah, you're putting these wacky great panels up in the airflow. Hideous amount of drag. Takes away all the lift from over the wings. So putting the weight of the aircraft fully onto the undercarriage improves directional control, improves braking, and as I said before, reduces the risk of aquaplaning. The flaps in the down position, again, is slowing the aircraft down on the runway, creating that extra drag. So now the aircraft should have slowed right down on the runway. We haven't had to use the brakes particularly, because it's all done aerodynamically. And then once the pilot pushes the throttle levers forward a little bit, the spoilers will automatically retract, and now he can taxi into where he needs to park up. Anybody got any questions there with the spoilers? No?
Excuse me, sir. Excuse me, Jim.
Yeah, shout at me, you're very quiet.
Can you explain the last line of this 46 page?
The last lines.
Yes, sir.
All right. Imagine that's the wing on my aeroplane. Yeah, I'm coming into land. The speed brakes are going to be raised to the full flight full flight extent because we're in the flight detent. So the aeroplane has slowed down to a suitable landing speed, and now I'm going to, well, the flaps are going to be lowered, to give me the lift over the wing. What I want to do is, when I'm on the ground, I want to destroy all that lift. Yeah. So in order to do that, to make sure that I'm ready for landing, I'm going to put the speed brake lever in the armed position. Yeah. That speed brake lever is connected to a little actuator, a little jack inside the console. So I'll put the speed brake lever into the armed position. So long as I'm in the armed position, I'm hot to trot. The aircraft will touch the ground. The aircraft will land. As the aircraft lands, the weight on wheel switches will make. So long as the weight on wheel switches have made, so long as the wheels are turning and the throttles are idle, the little actuator is going to drive the speed brake lever to the up position. Yeah. As it drives it to the up position, the flight spoilers will deploy to their fully up extent, and the ground spoilers will now deploy, and they will extend as well. So now over the whole length of the wing, I've got these metal plates sticking up, the spoilers. Yeah. So now any lift that I've got on that wing is going to be destroyed. The flaps, we said, are going to be down. I know they're in the wrong position, but because the flaps are down, yeah, that's going to slow the aircraft right down as well. Yeah, that's going to the airflow hitting the flaps. The flaps will go to their fully load position. The airflow hitting the flaps is going to create an awful lot of drag. Yeah, the airflow hitting the spoilers at their fully deployed extent again is creating an awful lot of drag, so you're not going to get any lift on the wing at all. Because you haven't got any lift on the wing, the full weight of the aircraft is going to be on the undercarriage units. Because the full weight of the aircraft is on the undercarriage, now if I'm using the brakes, obviously right at the end I'm going to use the brakes a bit, that braking is going to be a lot more efficient because the wheels are in contact with the ground. Yeah, the directional control, again, because I'm in direct contact with the ground, the directional control of the aircraft is going to be a lot more controllable. So as I'm moving the rudder pedals to make sure that the aircraft is going straight and level down on the runway, I've got better directional control. And the other thing is the full weight of the aircraft now is going to be touching the ground. Yeah, if I had that's not quite worked the way I wanted it, but if I had a wet runway, yeah, I'd have a layer of water on top of the runway. By putting the full weight of the aircraft on the ground, I'm breaking through that water and I'm in contact with the surface of the runway rather than the surface of the water, and that's going to reduce the chances of aquaplaning. Has that answered your question? Or not really? Hello?
Yes, sir. Thank you.
Yeah, you're happy with that, yes?
I'm happy.
Okay. Anybody else got any questions on that at all? Some aircraft, rather than using the spoilers as speed brakes in the air, some aircraft have separate air brakes to slow them down. Yeah, some transport aircraft they've still got spoilers. Yeah, the spoilers will act as lift dumpers and they will give roll control. Yeah, so on the aircraft that we're looking at on the screen, it's got 3 sets of lift dump spoilers. They will deploy when the aircraft touches the ground. The roll spoilers are there to assist the ailerons. And for slowing the aircraft down on the ground, we've got what they call air brakes. And the air brakes mounted on in this case, the rear of the fuselage. They make up the tail cone of the fuselage. And as the aircraft lands, the air brakes open. Yeah, they're opening and they'll open to a particular point, yeah, which slows the aircraft right down. Once the aircraft has landed, yeah, once it's fully on the ground, the pilot will select lift spoilers. The lift dump spoilers will fully deploy, and the air brakes will open out a little bit more, again to slow the aircraft down even more while we're on the ground. Yeah, so the air brakes form part of the tail section. 2 petal type air brakes hinged at the forward edges. They extend out either side of the fuselage center line. When they're closed, they form part of the tail cone. Operated using the selector switch in the cockpit. And that, I think, was about that. That's a good picture of a set of air brakes. The aircraft's coming into land. Yeah, he's selected his air brakes out, and that's going to slow the aircraft right the way down. Once he lands, yeah, everything on the ground, those air brakes will open out a little bit more, just to give him assisted braking and increased drag, slow the aircraft right down on the ground. And that, guys, takes us to exactly where we need to be for this morning. In fact, we're a little bit ahead of where we need to be this morning. Just so you know, this morning's or today's lesson is going to take us up to around about page page 68 is where I'm going to go. I'm going to finish the normal stuff, and what we'll do is we'll go over high-speed flight in the morning. Yeah, so we haven't got a hideous amount to do this afternoon, and it should be nice and steady. I'll give you fair warning. There is a possibility that we might finish a wee bit early because of the stuff we've got to do. So if that happens, if anybody's got any questions on anything that we've done so far this week, I know somebody emailed me yesterday. Rather than emailing me all the stuff, if you've got any questions at all, we've got a little window, hopefully this afternoon, where I can answer any questions that you might have. Failing that, I make it 12, just coming on to 12:10. So we'll start again at the usual time. It'll be 13:15 my time, which I believe is 1900 your time. Basic doodah. Just see if we can run. Basic aerofoil. Yeah, and as the air's flowing around the aerofoil, it goes past a certain point, yeah, and it will turn from laminar flow into turbulent flow. From then on, as it carries on down the aerofoil, it's slowing up, yeah, and eventually that air is going to break away, yeah, at the separation point. Behind the separation point, we've got no lift whatsoever. So what we want to do is to try and keep that boundary layer attached for as long as possible. Yeah. And the way we're going to do that is to re-energize it. We're going to get it flowing, and I don't know why that keeps spiking. So now what we want to do is to delay the separation for as long as we can. And that's what our boundary layer control is all about, really. Yeah, it's about making sure that we direct the boundary layer, keep it flowing. And the other thing that we need to do is to try and keep the flow of the air going chordwise rather than allowing it to drift spanwise from the aeroplane. So our boundary layer control then. The first thing it talks about in the notes there in section 9 is the stall wedge. Yeah, and the stall wedge is just a little device for tapered wings. Yeah, stall's going to start near the wing tips before it spreads towards the inboard end of the wing. And what we want to do with the stall wedge is induce any stall in the aircraft. We want it to start at the wing root. Yeah. So with your tapered wings, yeah, it's just a phenomenon of the tapered wing. If we get to the relevant angle of attack or slow speed, then the stall on the wing, the wing tip is going to start to stall first. With wing tips, there is no guarantee that one wing is going to stall at the same time as the other one. Yeah, there's always going to be a difference between them. When the wing stalls, it is going to drop very, very suddenly. It's going to lose all its lift, and that's going to flip the aircraft over, and the aircraft is then going to start to go into a spin. Yeah. Let's see if we can. Boom. There's my little aeroplane. Yeah, as we reach the stall angle, this wingtip is going to drop. It's going to drop rapidly. As that wingtip drops rapidly, the other one's going to rise. That's going to cause the aircraft to start rolling. As it does, this wingtip's going to start accelerating, moving forward very, very fast. Yeah, which in turn is going to increase the lift. So as it increases lift, and what's going to happen if you think back to your aerodynamics, your aircraft's going to start spinning. And once we're into a spin, unless we're a really good pilot and we've got a good aeroplane, it's very difficult to recover from. So the idea is to prevent the spin from occurring, or prevent the stall from occurring, I should say. So the stall wedge, or the spoiler strip on the leading edge of the wing root, is there to, when we get to higher angles of attack, it's going to disrupt the airflow at the wing root, and it's going to make sure that the wing root stalls first, stalls before the wingtip. In so doing, it causes a lot of vibration and turbulence over the aerofoil, and that vibration and turbulence would hopefully warn the pilot that he's getting towards the stall point. If he ignores it, then the wing root is going to do the stalling. And with the wing root stalling, it makes the aircraft easier to, in inverted commas, easier to recover. Spoiler strip, as it said, it needn't be a wedge like we see. What they can do is use these little inverted triangles and stick them on the leading edge of the wing, and they're going to have the same sort of effect. Yeah, as we get towards the critical angle of attack, the airflow over the wing root's going to be distorted and disrupted. It's going to cause all that turbulence, warn the pilot. Failing that, the wing root would stall rather than the wing tip. Yeah, it says that creates sufficient turbulence to energize the boundary layer and improve the effectiveness of the ailerons as well. And there's a bonus. Yeah, so as these little inverted triangles, yeah, as the air's flowing across, it creates turbulence, and again, another advantage is it's meant to cling to the top of the wing. So if you remember that the stall wedges and the stall strips are there to prevent the wingtip from stalling. Yeah, it's there to induce stall at the root of the wing. We won't go far away from there. Yeah. Another method of boundary layer control, the boundary layer breaking away from the rear part of the wing section because the air's slowed down, and it says it's flowing into a region of rising pressure. Yeah, remember the low pressure across the top of the wing. Yeah, again, we're going back to our aerodynamics. Yeah, as the air's flowing over the wing, you get a vast increase in the speed of the air. The velocity increases, so the pressure decreases. It slows down as it goes along the bottom of the wing, so you get a rise in pressure. But as they come to the trailing edge, was it Bernoulli? Yeah, the air starts to slow down, so you're going to get a rise in pressure towards the trailing edge. Yeah, and then when we get to the tip of the wing where the air comes off, you get the downwash, and the pressure is going to be equal. So what's happening as the air's slowing down? Yeah, that pressure gradient becomes less and less favourable. As the air slows down, it's not going to stick to the aerofoil. It's going to break away from the aerofoil surface at the separation point. Don't know why I'm going over this. Like you lot did module 8, and you were all geniuses. Has everybody passed module 8? No.
Yes.
Yeah, brilliant. Brilliant. Yeah. So
Just
what we want to
because
do.
Jim was there.
Sorry, say again.
Because Jim was there to teach us.
That's it exactly. I love you.
Big man.
Yeah, I'm pleased about that. Yeah, so it's nice to know things are successful. Yeah, so what we're going to do with our vortex generators then, yeah, we're going to put those on the top surface of the wing, and all they are little plates that stick up into the airflow, but the plates are positioned specifically. Yeah, and the purpose of the vortex generator is to ensure that the boundary layer speeds up as it flows across the top of the aerofoil. As that boundary layer is speeding up, it's sticking to the top surface for longer. Yeah, so it's not separating. We're not getting that that turbulence behind the wing. So we're reducing drag as well. Yeah, the vortex generators themselves are just little plates, and they're angled inwards against each other on the surface of the wing. I think we've got them on the top surface of the jet stream. Very, very common on aircraft. Like I say, they're just there, and they channel the air over the wing, but at the same time they cause it to swirl. Yeah. So what we've got, the vortex generators. They stick up they're just little plates. Sometimes I won't say aerofoil shape, but they're laid out in that sort of arrangement that you can see on the picture. As they protrude up into the airflow above the level of the boundary layer, they strike the uninterrupted air, if you like, and they cause the swirling effect, and it pulls air down into the boundary layer. As it pulls that air down into the boundary layer, obviously it's creating turbulence, and it's making the boundary layer speed up. And as the boundary layer speeds up, obviously that velocity is going to increase, and it's going to make sure that the boundary layer sticks to the wingtip for longer. Yeah. So your vortex generators induce faster moving air into the boundary layer, speed up the boundary layer airflow, and delay separation. And because of the layout of them, they're going to ensure that the airflow is flowing chordwise across the aerofoil, and not starting to move out spanwise. Yeah, forget that spanwise flow again. It's reducing the amount of lift that the wing's generating. So that's the idea behind our vortex generators. And again, just examples of them dotted out on the wing. Not a fantastic picture, but hopefully you get the idea. Again, from the notes, fitted on the top surface of the aerofoil, spanwise rows. Purpose is to speed up the boundary layer, prevent separation, reduce drag. Small plates, flat or aerofoil section, extend above in the air above the boundary layer, and make the free air turbulent. That drags it down into the boundary layer, increases the speed of the boundary layer, keeps it attached to the aerofoil for longer. Yeah, normally fitted in pairs. In pairs, each vortex generator, the pairs inclined at a different angle, and a number of pairs may be fitted along the aerofoil. May be fitted in front of a control control surface to make the control surface more effective as well. So the longer that air is sticking to the, where's my fucking arrow? Yeah, the longer that air's sticking to the aerofoil. Yeah, if you're in front of a control surface, you've got that re-energized air. Yes, it's going to make the control surface more effective. We know how they work and all that's dotted down there. Yeah. As it says, the vortex generators themselves do create some drag, but not enough to worry about. The advantages far outweigh the disadvantages. Reduced skin friction drag, yeah, which offsets the small amount of drag that they produce. Right, for because it's not on my slide for some reason, I don't think. At the bottom of page 50, yeah, it states there that vortex generators may occasionally be lost. They're just glued on normally, held on with some sort of adhesive. If we do lose a vortex generator, it may well be permitted to continue flying until we can replace it. To ensure that that is the case, we need to check with the MEL. So if you find a vortex generator missing, look in the MEL and that will tell you whether you're allowed to continue flying or not. That one sometimes crops up as well, so well worth sticking a highlighter through that. And again, the little picture under that, yeah, just showing how the vortex generators are going to keep the flow running chordwise. It's going to prevent that spanwise flow, and because we've got that accelerated airflow over the top of the aerofoil, it's going to make the control surface, whatever it might be, more efficient, more effective. Yeah. Swept wing aircraft, airflow tends to drift towards the wingtips, causing the boundary layer to thicken. Keeping it spanwise, yeah, by keeping it chordwise by using the vortex generators, we're stopping that spanwise slip. So it's acting as a barrier to the spanwise flow effectively. Yeah. Other methods we can use for a similar effect are wing fences. Yeah, the wing fence can wrap around the leading edge, or it can sit on top of the upper surface of the wing. Nice example of a wing fence there. And again, the wing fences are keeping the airflow moving in a chordwise direction. Yeah, they're stopping the airflow from drifting out into a spanwise flow, which again would reduce lift. Yeah, the wing fence produces a vortex, rotates in the opposite direction to the wingtip vortex. Yeah, so the wingtip vortex, whatever way that's going, the wing fence will create one going in the opposite direction. So again, we're reducing some of the drag that's being produced by the aeroplane. The vortilon is a wing fence, but the wing fence on the lower surface of the wing. It extends out in front of the wing, yeah, and high angles of attack, it'll generate a vortex over the upper surface. Yeah, so with your vortilons, what we can do on certain aircraft is bolt the engine to them. So the engine pylon, yeah, for some of your aircraft will act as a vortilon. So the higher the angle of attack, the more it's going to create this vortex over the top of the wing. Got that vortex, it's just keeping the boundary layer attached. Everybody okay with that? Yeah, so vortilon, a fence on the lower surface of the wing. Wing fences sit on the upper surface and sometimes wrap around the leading edge. Yeah, the vortex at the wing tip, the wing fence creates a vortex that runs in the opposite direction. So kind of reduces the effect of the drag. Another method of boundary layer control is what they call the sawtooth. Yeah, and the sawtooth gives a sharp change in profile of the leading edge of the wing. Yeah, that sudden change in chord, yeah, causes a strong vortex to form. As you get that strong vortex, obviously we've got that swirling over the wing. The other thing that sharp change in section does as well is keeps the airflow going in a chordwise direction and stops it eking out span-wise. Sawtooth leading edge, I've got to confess, the main ones I've ever come across have been on your military aircraft. That's not to say that there's not other aircraft out there with them, but that is a lovely example of how we can design our aircraft. So we've got that sawtooth. That sawtooth is going to keep the airflow running chordwise across the aerofoil. I used to work on those. Fantastic aeroplanes.
Nice.
So has anybody got any questions on boundary layer control? No? Lovely. Right.
If it is not coming in exam, we do not have any question.
It might do though.
Then please you ask us question. What type
Yeah,
of question will be coming?
like I say, I can't guarantee what questions they are. I've given you a breakdown of the questions, so you know how many questions are going to come. You know, so from theory of flight, high-speed flight, and the bits that I've told you to highlight are the more likely elements that are going to come.
Okay.
Yeah, so you know things like where would you find information regarding missing vortex generators? I'm not saying it's going to come up, but it's one of the more likely questions. As we said this morning,
more, Mr. Jim, we want more likely some such type of questions.
Yes.
I'm sorry, but I'm not here to try and relay what might or might not come up in the exam. Yeah, I'm giving you an idea of the sort of things that might crop up, but there's absolutely no guarantees that what I say will be. Yeah, but you've got the breakdown.
Yeah, we know
you
that.
know how many questions you're likely to see.
Yeah, we know that.
Yeah. People waiting in the lobby. Yeah, so you know, it could be something along the lines of where would I find the information regarding missing tabs? Certainly the axes are well worth remembering. They come up fairly frequently. What axis do the ailerons control the aircraft around? What axis would the elevators control about? Yeah, or elevators control the aircraft around what axis? Yeah, something along those lines. What else did we look at this morning? What's the difference between a slat and a leading edge flap? Yeah. If a delta wing aircraft was taking off, yeah, and he was rolling the aircraft during the climb, what position would the elevons be in? Yeah, so it could well be along those lines. Yeah, but as I say, there's no guarantees. I'm just trying to highlight, and that's why I'm reading the notes as I go through, so I can say page whatever, stick your highlighter through that. Okay.
Okay, okay.
Okie dokie, lovely. Right, so the next bit we're going to talk about then is trim. Yeah, trimming the aeroplane. We trim the aircraft to correct for a flying fault. Yeah, and again, we're on page 53. Yeah, the purpose of the trim tab is to correct for a flying fault. Worth highlighting. Yeah, a flying fault is the tendency of the aircraft to fly nose or tail heavy, one wing low, or possibly yawing in one direction or the other. Yeah, that is a flying fault. And what we're going to do is to trim the aircraft to correct for that flying fault. Sort of things that might cause a flying fault. Yeah, in yaw. Yeah, the aircraft might yaw to one side because it's got a single engine propeller, and the slipstream of that propeller is striking one side of the fin constantly. Yeah, asymmetric power, that could cause the aircraft to yaw. Yeah. Nose or tail heavy, yeah. The weight of the aircraft, as we are consuming fuel, the weight of the aircraft is going to change. Yeah, the CFG position is going to change, and the center of pressure, because the CFG is moving, the center of pressure might move. So that'll change the attitude of the aircraft. So we need to trim to correct for that flying fault. Yeah, consuming fuel. The arrangement of passengers, you might have 2 or 3 fat people like me on one side of the aeroplane, and a couple of skinny people like you guys on the other side. That's going to affect the attitude of the aircraft. So we'd have to trim the aeroplane to compensate for that. Yeah, positioning of cargo. If we haven't loaded the aircraft correctly, that's going to give us a flying fault, cause the aircraft to fly wonky. And certainly when we lower the flaps, as we discussed this morning, we're going to get a pitching motion. Yeah. So if we're going to be in that flap setting for any length of time, even coming into land, yeah, we'll need to trim the aeroplane to compensate for the position of the flaps. All okay with that? Yeah, so that's a flying fault. Yeah, we trim the aircraft to correct for a flying fault. If we developed a flying fault, let's say that the aircraft was flying nose down. Yeah, the way we could correct it is to pull back on the stick, and the pilot could hold the stick in the position that's going to keep the aircraft flying straight and level. But that is going to get very, very tiring. He's going to get knackered. He's going to be fighting the control stick. Just let me let these guys in. Everybody in? Yeah. Yeah, so holding the stick back to keep the aircraft straight and level, or holding the stick to one side to keep the wings straight and level, that would get very, very, very tiring for the pilot. So what we're going to do with the trim tabs is set the control surface using aerodynamic tabs. We're going to set the control surface to maintain the aircraft in that straight and level attitude. Yeah, there are 2 types of trim tab, fixed and controllable. Yeah, the fixed trim tab is, as the name suggests, it's dead easy. It is just a plate that's riveted onto the control surface, and then that plate is set at a whatever angle it needs to be for whatever job it's doing. Yeah. Alternatively, we've got adjustable trim tabs, and the adjustable trim tabs can be positioned from the flight deck, from the cockpit. Yeah, anything else on it? So the fixed trim tab, yeah, only corrects for flying faults at 1 speed, normally found on light aircraft. Again, that sentence, yeah, your fixed tab corrects flying faults at 1 speed. Whack a highlighter through that one. That's come up before now, page 53, just above the pictures. Yeah. Controllable tab, yeah, is hinged, as the picture suggests, hinged at the trailing edge of the control surface, and we can adjust that tab's position from the flight deck using cables, chains, push-pull rods, whatever. Some trim tabs we can use an electric actuator on them and switch on top of the stick, which we'll go into in more detail probably tomorrow. Yeah. The tab is going to move the control surface so that the aircraft moves in the instinctive manner. So if I'm flying, let's say nose down, Ben, yeah, aircraft tendency to fly nose down, yeah. So the elevator needs to be placed in an up position to push down on the tail to bring the nose back up. To position that elevator, yeah, if I've got a tab on the back, I'm going to put the tab down. Putting the tab down is going to push the elevator up. Pushing the elevator up is going to push the tail of the aircraft down, which is going to bring the nose up, which is correcting the flying fault. Yeah. With your fixed trim tab, yeah, we're only going to be able to correct that that fault at 1 speed, as it said before. So your fixed trim tabs, they take a bit of setting up, but once they are set, that's it. We can kind of forget them. The controllable tabs, obviously, a lot more of an advantage there because we can alter the position of them relative to the attitude of the aeroplane. So that's the idea of your fixed trim tab, just a metal plate riveted onto the back of the control surface, and then we just bend it to the selected position. When I say we bend it to the selected position, there are special tools for bending these things. We don't just get 2 pairs of pliers and twist, but there's special tools for setting them. Once we've done that, the aircraft's got to go up, aircraft's got to fly. Pilot will come back down and say, oh, well, it's flying flying too much to the left, so we'll adjust the trim tab again, just bend it slightly, send it back flying. Pilot will come down and say, no, you've gone too far, so we'll move it the other way. As I say, once the thing's in position, we can forget about it, but actually getting it there can be a bit of a pain. Controllable tab, hinged trailing edge, yeah. Control is instinctive. The tab will correct flying faults at all speeds. Small, simple aircraft types may have fixed tabs on the ailerons and rudder, but they would all aircraft would generally have a controllable tab on the elevator. Yeah, most of your flying fault is going to be around the pitch, so the cargo, fuel, all the rest of it. So most, I'd say 99% of aircraft have got a controllable trim tab on the elevator. Yeah. Adjustable trim tab, controllable trim tab. Yeah, and that's it on the elevator. And from the flight deck, we can position that up or down. If we have it up like this, yeah, that's now aerodynamically forcing the elevator down. Because the elevator is forced down, we're getting an uplift on the tail of the aeroplane, which is bringing the nose of the aeroplane in a downward direction. Ta-da! Okay. what we're doing then, yeah, the aerodynamic force acted on the tab, as I tried to show you just there, is producing that turning moment, and that's keeping the control surface in the required position so that the pilot doesn't need to do anything from the cabin. Yeah, he can set that tab in the right position, take his hands off, have a cup of coffee, read the newspaper, whatever, and the trim tab will maintain the aircraft in the correct attitude. The trim tabs are controlled from trim wheels in the flight deck, and the trim wheels are set up so again they're in an instinctive direction. The elevator trim wheel normally on the side of the throttle quadrant, the center console, yeah, and that turns forwards and rearwards. If we turn the trim wheel forward, it's going to bring the nose of the aircraft down. If we turn it rearward, it's going to bring the nose of the aircraft up. So that is our instinctive direction. Left and right, yeah, again, the trim wheel set up in the same axis, if you like, as the plane we want to move it in. So if I move the trim wheel to the left-hand side, yeah, it's going to bring the right-hand wing up, which is going to level the aircraft. If I go the other way, same sort of thing's going to happen. The right-hand wing's going to go up, the left-hand wing's going to lower, again, balance the aeroplane. The rudder trim wheel set up in a vertical plane. Yeah, so if I turn it left, it's going to move the aircraft to the left. If I turn it right, it's going to move the aircraft to the right. Yeah. How does it work? Yeah, well, on the you got your main surface, let's say tailplane, just for argument's sake. At the back of the tailplane, we've got the elevator, and on the back of the elevator, we've got the trim tab. I put an input into the trim tab. Yeah, the tab goes up, elevator comes down. Yeah, so aerodynamically, I've created that upper surface camber. The concave, I've increased the pressure. That's going to push down, so the elevator is going to get pushed down. Yeah, as the elevator's pushed down, that in turn is changing the camber between the elevator and the main control surface. And again, that pressure that we talked about before, the whole tailplane is going to rise. So as the back of the aeroplane rises, the tail rises, the nose is going to come down. Once I've set that tab in position, the elevator will remain in that position. Yeah, and now the attitude of the aircraft is going to remain in place until I move the tab again. By moving the tab, it's going to alter the position of the control surface, and again, that's going to affect the attitude of the aircraft. Yeah, the control surface moves in the opposite direction to the trim tab, and the control wheel again moves in the instinctive direction. Yeah. So, fat, dumb and happy. Yeah, I need to alter the attitude of the aircraft, turn the wheel in the cockpit, bring the trim tab down, which in turn is bringing the control surface up, which in turn is creating a pressure on the whole tail, which is going to push the tail down, bring the nose of the aircraft up. So by winding the trim wheel backwards, I'm adjusting the position of the trim tab. The control surface is moving in the opposite direction to the trim tab, which in turn is bringing the whole aerofoil into the desired attitude for and keep the aircraft straight and level. Okay with that one. So there's your, I could have saved myself a lot of grief, couldn't I? There's your horizontal stabilizer, there's your elevator, there's your trim tab. Move the tab. Yeah, tab goes up, elevator goes down. Elevator goes down, the nose of the aircraft is going to come down because the horizontal stabilizer is being pushed up the way. Want to trim nose up? yeah, wind this control wheel back, yeah, tab goes down, which in turn aerodynamically forces the elevator up, which in turn creates that pressure on the tailplane, pushes the tailplane down, and the nose of the aircraft comes up. Everybody okay with that? Easy enough? Example that gives in the notes, it looks at an aileron trim tab. Yeah, turn the trim wheel. Yeah, aircraft flying, let's say left wing low. Trim tab on the left-hand aileron's moved up by rotating the trim wheel to the right. Left aileron's lowered, right aileron rises, and that corrects your flying fault. If the aircraft's flying right wing low, yeah, trim tab on the left aileron's moved. Move the trim wheel, left aileron raised, right aileron lowered, and again that corrects it. So on your ailerons, yeah, you're only going to have the one trim tab, because whatever the input on the left-hand wing, the right-hand wing's going to do the opposite, isn't it? Yeah. So yeah, your trim tab on your ailerons, you just got one. It doesn't matter really which aileron it's on, but all we're going to do is turn the wheel. That's going to position the trim tab. Positioning the trim tab is going to move the aileron aerodynamically, and that's going to adjust the position of the wing, again to bring the wings level and keep us in straight and level flight. Same thing, just the opposite direction. Elevator trim we've already looked at, so moving the trim wheel rearwards, yeah, it's going to move the trim tab. As the trim tab repositions aerodynamically, it's moving the elevator. Moving the elevator, we're getting a downforce. We've moved that wheel back, so we want to bring the nose of the aircraft up, and that's exactly what's happening. The trim tab positioning the elevator and holding it there to keep the aircraft in a nice level attitude. And again, the opposite for our elevators. Elevator forward movement, the trim wheel moves the tab up. Elevator lowered, gives a nose down trim change. Exactly the opposite when we move there. Happy days, yeah. The rudder trim wheel. I'm just going back over what I was saying there about the trim wheels moving in the natural direction, the way they're set up. Yeah, that in the cabin. Set up so it's a fore and aft, left and right movement, and then with your rudder, yeah, again it's in the same plane. Move it left. I'm causing the tab to move. The tab's going to move the rudder for me, which in turn is going to move the tailplane to give me that straight attitude. Yeah. Yeah, so the rudder trim in the cockpit mounted so it rotates about a vertical axis. Nose right trim, move the trim in the clockwise direction. Nose left, anti-clockwise, and then the movement of the tab aerodynamically moves the rudder for us, the control surface. Some aircraft trim tabs are moved electrically, so we're going to use a little electric actuator, a little electric motor, rather than a mechanical wheel. Yeah. The switch in the cabin spring loaded to the center position, the off position. Yeah, the switch again exactly the same as the wheels. It's operated instinctively. So if I push the switch forward, nose of the aircraft's going to come forward on the trim, on the pitch trim. If I move the aileron trim switch to the left, the aircraft is going to sort of roll towards the left. Move the left wing, move the right wing up to left wing down to bring us back to that straight and level. Yeah, once we've positioned the tab, it will remain there until we need to change it to renew the position. Yeah, your flying fault, again, we've said this before, it's the tendency the aircraft has to fly nose heavy, tail heavy, one wing low, or yaw. Yeah, and we've said that the different reasons that we might get a flying fault. Yeah. One wing low, yeah, it could be that you've got an aileron drooping, an aileron damaged, damage on the main plane or the flaps. If the flaps aren't set up properly and you've got a flap drooping, again, that's going to introduce a rolling tendency. Light aircraft, the incidence of the high wing could be too great. Yeah, incidence on the low wing could be insufficient. Again, that could be your ailerons not rigged properly. Whatever, but it's causing that wing attitude. So by moving the trim tab, we're correcting that fault. Leading edge pneumatic de-icing boots, yeah, if they've not deflated properly, they're going to spoil the airflow over one wing. So again, because we've got less lift on one wing than we have on the other, we might need to trim the aircraft to bring it nice and level again. And the other favourite one is poor fuel feed from the fuel tanks, yeah, causing that imbalance. Your flying faults, yeah, correcting the flying faults, and we've been through that. I'll let you have a look through that in your own time, but it's just showing what the fault is, which way we need to move the hand wheel, and which way that's correcting the aeroplane. Yeah. Again, we've been through. We don't need to worry too much about that. Slipstream. Yeah, the slipstream from the propeller wraps itself around the aircraft and then strikes the rudder on one side or the other, depends which way your propeller's rotating. But as it strikes the fin of the aeroplane, it's going to cause a yawing motion. That yawing motion we can correct for by either a fixed tab, a controllable trim tab, or what they sometimes do is actually offset the fin. They change the position of the fin slightly to compensate for that slipstreaming effect. Yeah, again, it's just another method of trimming the aeroplane. Offsetting the fin is pretty much like using a fixed trimming tab.
Hello.
Hello? Right.
फ्लाइट प्रोग्राम दिन्छै आइहाल्छ यो कम्पनीमा।
सञ्जय दाइ तपाईको माइक एकपल्ट अफ गरिदिनु पर्यो।
Hello? Just let me let the man in. Milan. There we go. Milan has joined us. Just at the right time. Right, looking through there, nothing we need to worry about. Just example of how the trim tabs are correcting for that flying fault, keeping the aircraft in a nice straight and level condition without any input from the pilot. Yeah.
Can you say again, Jim?
Yeah, the trim tabs are there to correct for our flying fault. Yeah, so if we're nose heavy, tail heavy, we're going to move the trim handle. Yeah, in this case, let's say we're nose heavy, we're going to move the trim handle rearwards, which is instinctive to bring the nose up. Yeah, the trim tab is going to move. The trim tab is aerodynamically going to move the elevators, and that is going to push the tailplane down to bring the nose up. Yeah, so we're correcting that flying fault using the trim wheel. The pilot can set the trim tabs, is controllable trim tabs, and that will keep the aircraft straight and level until we move the trim tab again or the flying fault reoccurs. So if you think of something like your pitch trim, yeah, the aircraft flying nose heavy, yeah, I'll move the trim handle back. That'll move the trim tab, bring the nose of the aircraft up, and that will stay there like that. But all the time I'm flying along, I'm consuming fuel. And as I'm consuming fuel, that is going to affect the trim of the aircraft. So I'm going to have to adjust the position of the trim tab a bit later on. So it's there to keep the pilot, reduce the pilot's workload, but you know it will need to be adjusted again during various stages of flight. The fixed trim tab is just going to hold you there one speed. We mentioned that. And slipstreaming, yeah, if you've got a single propeller aircraft, and it's worth remembering this, the single propeller is going to create a slipstream, and the slipstream is going to wind its way around the aircraft and strike the fin on one side or the other, depends which way the propeller's turning. But as that slipstream strikes the fin, it's going to push the tail round. It's going to cause the aircraft to yaw. Yeah. So we can either use a fixed trim tab to compensate for that. We can use a controllable trim tab, or sometimes what they do is offset the fin. So the fin isn't in a straight line with the aircraft. It's slightly offset. And that has the same effect of trimming the aeroplane.
So Jim,
Yeah.
There are in this paragraph slipstream effect. There are two lines with a left-hand tractor puller propeller. This is on the right side with a right-hand tractor puller. This means this terminology, left-hand tractor propeller, is that means the rotation of the propeller is to left side, and with the right, is that means?
Yeah. So the left-hand propeller will be turning in a clockwise direction.
Yes.
The right-hand, propeller on the will be going the other way. Yeah.
The left-hand propeller will be turning on clockwise direction. Yes.
Yeah.
Yes.
Like I said, it doesn't really, we don't need to worry about that. We're just saying that whichever way the propeller's turning,
yes,
the slipstream is going to wind around the aircraft, and it's going to hit the rudder on the fin on the left-hand side, or if it's going the other way, it's going to hit it on the right-hand side.
So in this picture, the propeller is turning on left-hand side.
Yeah, it looks it, doesn't it? Is that turning it's turning clockwise, isn't it?
Yes, it's turning clockwise.
You take the attitude of the aircraft, so that is turning. Clockwise.
That is left. So the rudder offset is towards the right.
Yeah, well, whichever way the propeller's turning. In this case, the propeller's turning this way. It's causing the slipstream to go around the aircraft, and it's hitting the right-hand side of the fin.
Okay. Okay, Jim, it's okay.
So that would be left the way because it's striking the.
So
striking the fin
in
on
this
the right
case,
side.
in this case, offset is towards left side.
Yeah.
So the slipstream is striking on the right side.
Yeah.
Okay. And the left hand propeller is on the right side. Yes, on the right hand propeller. Okay, Jim. Thank you.
Yeah. So as this is turning, it's causing that slipstream to wrap around the aircraft, and it's striking the the right hand side of the fin. Yeah. So that's turning in a left hand direction, anti-clockwise direction, isn't it? Okay, right. So that was trim. Trim to correct for a flying fault. Yeah. When we now come on to aerodynamic balance, yeah, what we're talking about with aerodynamic balance is the pilot moving the control surface. As he moves the control surface, the aerodynamic forces are going to be trying to oppose what he's doing. So aerodynamic balance, yeah, we're going to use tabs to help the pilot move the control surface. Yeah. So aerodynamic balance is assisting the pilot. When we talk about anti-balance, we're providing resistance to his movements. Yeah. So, yeah, your elevator, yeah, large aircraft, we've got a balance tab on the elevator. So as the pilot moves the elevator, we're going to use that tab to aerodynamically help him to move the elevator. Yeah. As he's flying along, the aerodynamic loads would be a bit much for him. Yeah, he's only got so much strength. So by giving him that aerodynamic assistance, we're just making movement of the control surface a bit easier for him. Yeah. And again, it's just showing how that aerodynamics is working. We'll not move, not worry too much about that. Yeah. Yeah. Product, the aerodynamic force acting through the center of pressure of the surface and its distance from the hinge line will produce an opposing moment, known as the hinge moment. Yeah. Magnitude. Yeah. Aerodynamic balance is a means of reducing the effort that the pilot needs to operate the controls. That's on page 60, about halfway down. Yeah. Stick your highlighter through there so that there's no mistaking what aerodynamic balance is. Means of reducing the effort that the pilot needs to move the controls. Okay with that? Yeah, there are different methods of achieving aerodynamic balance. Yeah, we can use a horn. Yeah, we can use an inset hinge. There are internal balance panels, and we can use tabs, all designed to assist the pilot. Yeah.
Jim.
Yeah.
The tab which we just studied earlier, trim tab and elevator tab, these are the not of the part of the aerodynamic balance.
No, the trim tab is there to correct for a flying fault. The balance tab is there to help the pilot to move the controls.
Okay.
Yeah. Yeah. So to help him move the controls, we're just coming on to there are different methods. One of the methods is to use a tab. Another method is to use horn. Yeah. So as the pilot moves the control surface from the neutral position, as the control surface moves, the horn sticks out into the airflow, and the airflow pushes the leading edge of the horn around, which in turn is moving the trailing edge. Yeah. So as he's again flying along, yeah, tries to move the control surface, you've got the airflow, yeah, resisting that movement. Yeah, so as the pilot's pushing down on the, let's say, a rudder pedal, we're looking down from the top. He's pushing on the rudder pedal. Yeah, the airflow is trying to push the rudder back the way, but because we've extended the leading edge out, the airflow on the other side now is giving us a pushing motion, and it's helping the pilot to move the control surface. Yeah, so that extension of the leading edge. Yeah. Same with this one. Yeah, on the aircraft here. Yeah, we've got the horn tip. Yeah. So now as the pilot is trying to move the elevator, the airflow coming across is trying to push the elevator back down. But by allowing the horn to protrude into the airflow, yeah, the airflow is pushing the horn down, which in turn is helping the pilot to move the elevator in the upward direction. So that's what we're talking about when we talk about aerodynamic balance, assisting the pilot. Some of the methods that we talked about, yeah, these horns, yeah. If you imagine you're looking down on top of a tailplane, or imagine you're looking at a fin, yeah, yeah. Again, as I say, you know, as the pilot's pushing on his rudder pedals, the rudder's trying to move, and the leading edge of the rudder in the airflow is being caught by the airflow and helping him move it. Yeah. So we get these horns, the unshielded variety, like this. Hopefully you could see the unshielded horn there, the unshielded horn there. The shielded horn, just the nose of the thing, yeah, is just inset, so it's not interfering with the airflow during normal operations. Yeah, so you're shielded and you're unshielded. Yeah. The inset hinge, if you're looking down on top of, let's say it's an aileron, yeah, the hinges are flush flush with the top surface. Yeah, as I'm looking down on the top surface, yeah, everything is nice and flush. As I move the aileron, as the aileron comes down, the hinge fingers start to protrude into the airflow. And because they're protruding into the airflow, they're helping to move. Again, I'm not sure if you guys can see my picture, but the inset hinge is something like that. So now, as I try to move the control surface down, the hinge starts to stick up into the airflow. The airflow striking the hinge is going to help to move the control surface. Does that make sense? Can you say that? Harry, you've got your hand up. Is that a question?
Jim,
Harry?
Jim, can you hear me?
Harry? Sanjay, yes, are you talking to me?
Yes, sir.
Yeah. What can I do for you?
It look like a hinge, inset hinge and phase generator look like the same.
Say that again. Yeah, turn your mic up. I can't hear you.
Inset hinge and phase generator look like the same.
Similar, yeah. Yeah, they're having the same effect. Yeah, the hinge, as if that's my control surface, as my control surface is moving, the hinge starts to sit up in the airflow, and the airflow is going to help to move the control surface. With your horn, you're having the same effect.
Thank you.
There was the next one, Yadav. You have your hand up, sir. Surrender. No.
Yeah, I'm okay.
Okay then. Everybody else okay with that? Any questions there? So that is a type of aerodynamic balance. Yeah, the horn balance, the horn tip, the shielded horn. Yeah, the inset hinge just works exactly the same as the horn tip. All that's happening is the leading edge of the hinge is coming up into the airflow, and the airflow aerodynamically assisting us to move. What we'll do there, I'll make that 14:20. We'll just have 10 minutes and then I'll finish everything off. Okay. So we'll just have a 10-minute break there, and then we'll finish the rest of the thing off. Okay with everyone?
Okay.
Oh, okay.
Okay, 10 minutes, and then we'll finish all off. I'll see you in a minute.
Hello, Jim.
Yeah, hello?
Hello. Are you there?
Yes, I'm here.
Okay, it's a break time, but if you don't mind, can you repeat the boundary layer control just for me?
Yeah, what I'll do, I'll go back to after break, and then anybody else that needs it, I can do it all as a one.
Okay, then okay, no problem.
Okay, so yeah, I'll go back to boundary layer before we finish.
Okay, thank you.
No worries. Yeah, enjoy your ride. Yeah. Right then, guys. We were looking at aerodynamic balance. Somebody asked me to go over boundary layer again, a couple of bits. Just wanted to recap. So what I'll do, I'll finish this bit on balance, and then at the end I will go over boundary layer. So if anybody else needs to go through it with me, that's absolutely fine. Okay, so right, balance then. Yeah, we said that aerodynamic balance is assisting the pilot to move the controls. We looked at the horns, the protrusions that go out into the airflow and help give that twisting moment to the, or not twisting, but that turning moment to the control surface. And another method that we use on some aircraft is what they call the balance panel. Yeah, and the balance panel is just a little, as the name suggests, a little hinged panel that lives in the, pardon me, the rear of the wing, behind the wing spar, connected to the control surface. As we move the control surface, it opens up a slot to the air. As that slot opens up, yeah, we're going to get air pressure acting on the balance panel. Just a little metal panel. We get air pressure acting on it, and the air pressure acting on the panel helps the pilot to move the control surface. Yeah, so we're using air to help him. Yeah. So in this turn, we're trying to move the thing. Yeah, got your balance panel. Air's going to come here. Air's going to press down on the panel. Pressing down on the panel is going to push the aileron up. Same here. Yeah, air coming in, pushes down on the panel, pushes the thing up, and obviously the area below the panel, there's less pressure there, so the aerodynamically we're assisting the pilot to move the control surface. The other type of assistance we can give him is with balance tabs. Yeah, the tabs hinged to the trailing edge of the control surface, connected by a rod to a fixed part of the main structure. Yeah, so you've got your little rod there, fixed the main structure. The pilot putting an input into the control surface. Yeah. When the control surface moves in one direction, the tab automatically moves in the opposite direction. So the aerodynamic force acting on the tab produces the turning moment, which helps the pilot to move the control surface. As I say, pushes the control surface down. Yeah, as he pushes the control surface down, because of this fixed rod, the balance tab goes up. And now you've got that curvature that's helping push the control surface down. Yeah. In neutral, the balance tab will sit there. It'll be trimmed, fed with the main control surface. Pilot makes his input, pulls on the stick. Yeah, pulls on the control surface. As it does, that fixed rod is now pulling down on the balance tab, and the positioning of the balance tab again is creating that camber, that pressure, which is pushing up on the control surface. So what he's doing as he moves the control stick, yeah, the balance tab's moving in the opposite direction, and it's helping him to move the control surface. Again, same sort of thing. What we can do as well is pair up the balance tab with the trim tab. So a trim tab and a balance tab we can have one tab performing two functions. Yeah, so the balance tab, the trim tab. If I've set the trim tab to correct for my flying fault, if the pilot makes an input, again the fixed link is going to move the balance tab, help the pilot move the controls. When the control surface goes back to its original position, the trim tab will return to its original position. So we can have one tab performing two functions. Anti-balance, yeah, the anti-balance tab is there to resist the movement of the pilot. The anti-balance tab is there to help protect the aircraft from being over-maneuvered and overstressed. Yeah, so the anti-balance tabs, there are different types of anti-balance tab, but the geared tab is the one that we look at. The geared tab, yeah, you've got your control surface, the tab in the neutral position. Yeah, as I move the stick in one direction, yeah, up to a certain point, the tab is now being pulled down. It is providing a balance effect. It's helping the pilot to move the controls. Then via the gearing, as I go past a certain point, yeah, the tab flips over, and now it's providing an anti-balance. Yeah, it's resisting the movement. So I can move the control surface so far with aerodynamic assistance. That helps me. But I go past a certain point, yeah, and now aerodynamically, the movement of the pilot is being resisted. Same in the other direction. Yeah, we've got the tab. Pilot moves the stick. Yeah, the gearing in the tab moves the tab slightly up, which is helping to push the control surface down. Go past a certain point, the gearing mechanism kicks over, and now the tab is being pulled down, and that is giving that anti-balance. It's protecting the pilot against protecting the aircraft against the pilot's input. Yeah, that's the geared tab. Yeah. Not a lot else I need to say there. The servo tab, hinged on the trailing edge of the control surface, tabs connected to the controls in the cockpit, so it's the tab that's directly controlled by the pilot. Yeah, when the aircraft's flying, there's less effort required to move the tab into the airflow than would be for the main surface. So the aerodynamic forces acting on the tab, yeah, cause the control surface to move. Yeah. So if you think of servo, servant, slave, yeah, it's by moving the tab, and the tab creating that aerodynamic movement for the control surface. That is your servo tab. Yeah, and again, it goes in the opposite way. If a pilot pulls back on the stick, yeah, he's pulling back on the tab, and it's the action of the tab that's causing the control surface to move. The servo tab. Spring tab's similar to the servo tab, but we've got springs in the control system so that low speed, the pilot's got direct control moving the main control surface. Above a certain speed, the aerodynamic force resisting the movement of the control surface will overcome the spring pressure and allow the tab to be operated. So the aerodynamic force on the tab is now giving us that turning moment and helps to move the control surface in the required direction. Yeah. So we've got direct control at slow speed and the tab control at higher speeds. Again, just showing the tab, the control link via the control surface and the little lever. You've got a spring in there. So move the control surface at low speed. Yeah, I haven't got the aerodynamic force fighting against me, so I can move the control surface. At higher speeds, there's a much greater aerodynamic force, so the input that the pilot's putting in causes the spring to compress, and the action of the spring compressing allows the tab to move. So at higher speeds, the tab is there to give aerodynamic assistance to to moving the control surface. That's your spring tab. Anybody got any questions there? Mass balancing.
Hello, Jim.
Yeah.
Jim.
Yeah.
Can you again describe this geared balance tab?
The geared tab, yeah. Yeah.
Yes.
That one, right? Your geared tab, yeah, is just a little lever, a crank, and a rod that's attached to the tab.
Okay.
Just let these guys in. When we're in neutral, the tab is fed with the control surface, everything happy. Yeah. If I move the control surface, initially I'm going to get the tab moving to help me move the control surface. So initially, as I move the stick, yeah, the gearing moves round, yeah, and it moves the tab into a balanced position. So now the aerodynamics is helping to push the control surface down.
Okay.
Yeah. I'll get to a certain point, yeah, and now that gear is going to click over. Yeah, and it's going to cause the tab to move in the opposite direction. So now the airflow is pushing against the tab. The airflow is trying to push the control surface up. Yeah, so it's making movement of the control a lot more difficult. So it's having an anti-balance effect, and that's going to protect the aircraft from over maneuvering and over stressing.
Okay.
You okay with that?
Okay.
So the point to remember here is the gear tab is for both balance and anti-balance.
Yes.
Okay. Thank you.
Okay.
Is hello, Jim.
Yeah.
In this case also, is there any I think speed is not related for changeover of this, but angle is more related. At certain
in as
angle.
much as the further you move that control surface down,
yes,
yeah, you're going to have the balance effect till you get to a certain point. Yeah, then the gearing is going to click over, and it's going to cause the tab to move in the opposite direction. So rather than the tab being up, it's getting pulled in a downward direction now. So what effectively is happening is you're preventing the pilot from moving that control surface too far.
Okay, got it, Jim. Thank you.
Yeah. Anybody else? Servo, yeah, we know about that. Spring tab. Mass balance. Yeah. What's happening with mass balance is the let's see if I got my picture. Yeah, the hinge line of the control surface wherever it's fitted. Yeah, the hinge line. What can happen, because we've got a large area behind the hinge, yeah, and the center of gravity is aft of that hinge, and because of that, yeah, because of the center of gravity position, what can happen is the control surface can start moving, and once it starts moving, fluttering, yeah, it will start to vibrate. It will send that vibration through the aircraft structure, and the aircraft will become quite uncontrollable up to a point. So to counteract that, what we need to do is to bring the center of gravity as far forward as we can to prevent that movement at the trailing edge. And the way we do that is to put a weight forward of the center of gravity, yeah, forward of the hinge line. And that's our mass balancing. Yeah, just putting a weight forward of the hinge line to prevent the trailing edge from going into flutter. Yeah. So because of the flexibility of the aircraft structure, and again, I'll see if I can find that little YouTube clip that I was talking about and just show you before we finish. The vibrations increase in frequency with an increase in speed. Flutter is that high frequency vibration. And once we get to a certain speed, that flutter will increase violently. So unless the speed of the aircraft's reduced, yeah, the flutter may cause the aircraft structure to break apart. And those control surfaces are affected as well. So if the centre of gravity of the control surface is behind the hinge line, the acceleration will move the control surface relative to the main aerofoil surface. In other words, yeah, if we didn't have the weight forward of the hinge, the trailing edge would just start banging up and down like nobody's business. Yeah, that's where your flutter sets in. So the way we prevent the flutter is just to put a weight forward of the surface hinge, brings the centre of gravity as near as we can to the hinge line, and that process, that fitting of a weight, is known as mass balancing. The mass balancing, the weights that we use, yeah, we'll put them forward of the hinge line on a horn or in the front of the control surface, and you can see in this one at the horn somewhere in here, somewhere forward of the hinge line, we're going to put these weights. Yeah, the horn that we've got on this is bringing the weight forward of the hinge line, and that process is known as mass balancing. The stuff that we use for the mass balance is weights, and those weights are made out of a small but heavy material such as lead. Tungsten we can use, or depleted uranium. Yeah, really nice stuff. Lead, they're crying away from now because it's quite toxic, lead. Tungsten's not bad. Depleted uranium, yeah, although it's theoretically slightly radioactive, you know, it's a nice dense material, and it does a perfect job for our mass balance. Anything else I need to say there? No. Yeah, the weights themselves, yeah, internally along the leading edge, as we said, inside the horn balance, or on your protruding arm that brings it forward of the centre line. If you just give me 2 ticks. Hopefully you can you can't hear anything, can you?
No, Jim.
This is a bridge in America that got flutter set into it. I'll skip round this in I'll skip round the bridge in a minute. I'll just let you see what happened to the bridge, but the ins and outs of it. Okay, can you hear me? Okay.
Yeah, Jim.
Yeah.
But no sound.
Can you hear that?
Not yet.
No sound. This is flutter anyway. It's where the aircraft starts vibrating. Yeah. And as you can see, if we don't do anything about it, it can get really, really nasty, really serious. That's a good clip for that flutter. This is flutter that happened to a bridge in America. Exactly the same principle. The harmonics set in, and once that vibration had started, unless the speed of the aircraft is reduced, there's nothing we can do about it.
Jim.
Yeah.
Can you please send the link of the this video so that we can watch some other time?
Yeah.
Okay. Thank you.
What I'll do, I'll send it to Yadav and he can pass it on to you.
That will be okay.
Sure.
Okay.
Eh?
Okay. Thank you.
Yeah, I'm not sure how to do it otherwise. And hopefully that's got to you already. Right, that was the basics, the mechanics, the first bit that I wanted to cover today for our theory of flight. Yeah. So if anybody's got any questions, and just for whoever it was, I can't remember who asked now, but boundary layer control. What we're doing with boundary layer control is we are keeping the airflow attached to the aerofoil for as long as possible to help us with the drag and all the rest of it. And we're going to keep the airflow flowing over the aerofoil in a chordwise direction, because we don't want it sliding off span-wise if we're going to avoid it. Span-wise, if we let that happen, we're reducing lift and we're increasing the drag on the aeroplane because of your vortices and all the rest of the shit. With our tapered wing aircraft, yeah, the tapered wing aircraft, if we get to the critical angle, the stall angle, and that's him. Shiranjivi.
Yeah.
Control.
I just left out of the room.
Yeah, boundary layer control. What we're doing, as the name suggests, we're just controlling the boundary layer flowing over the aerofoil. Yeah, with the tapered wing aircraft especially, but smaller, lighter aircraft. Tapered wing aircraft especially, a stall, once we reach the critical angle, the stall will start at the wingtip. And the last thing we want is for the wingtip to stall, because it'll lose lift very, very quickly, very suddenly. The wing will drop and the aircraft can enter a spin. And a wingtip stall is very, very difficult to recover from. So what we want to do is to encourage the, if we do get to the stall point, we want to encourage the root of the wing to stall first. One of the ways we can do that is to put a spoiler strip on the leading edge. Hopefully see it on the slide there. That spoiler strip is going to, as we get towards the critical angle, it's going to disrupt the airflow over the root of the wing. By disrupting the airflow of the root of the wing, we're encouraging the root to stall before the wing tip. Yeah. The other thing with leading edge spoiler strip is the disruption of the airflow, creating that turbulence, is going to set up vibration in the aircraft, and hopefully that vibration will warn the pilot that he's approaching the stall angle. Another variation is these little triangular strips that we can put on the leading edge, and again with those things we're going to disrupt the airflow. Disrupt the airflow. Sorry, yeah, create turbulence over the top of the aerofoil and re-energize that boundary layer. Again, that turbulence, we might get it severe enough to cause a bit of vibration, but ideally what it's going to do, it's just going to create turbulence across the aerofoil and give us a bit more control. It's going to energize that boundary layer, and depending on where we've positioned them, increase the efficiency and the effectiveness of the ailerons. The vortex generators are little metal plates that stick up into the airflow. They're arranged in pairs, various points on the upper surface of the wing. And again, the vortex generators are there to ensure that the airflow is maintained in a chordwise direction, and they also speed up the boundary layer, keep the boundary layer attached for longer. Yeah, your vortex generators, yeah, as we said, laid out there in pairs. You get them in front of the control surface, and what they're doing is that as the airflow goes through the pairs of generators, yeah, it's being kept flowing in a chordwise direction, but at the same time, the generator sticks up into the airflow, protrudes just above the boundary layer, and the free air above the boundary layer, the generator causes it to swirl. It drags it down into the boundary layer. As it drags it down into the boundary layer, it's causing it to speed up. Yeah, and that speeding up of the boundary layer is obviously delaying the separation point. The longer the air sticks to the aerofoil, the more lift we generate and the less drag we generate, and yada yada. Yeah, those are your vortex generators, directing the airflow, stick it up in, yeah, creating that turbulence. Turbulence increasing the speed, and because we're increasing the speed, we're keeping the airflow attached to the control surface for longer. Other methods we're going to use for a similar effect are wing fences. Yeah, the wing fence sits on the upper surface of the wing. Sometimes it'll wrap around the leading edge. And again, that's going to keep the boundary layer flowing in a chordwise direction. But the shaping of the wing fence also causes a vortex behind it. And that vortex runs in the opposite direction to the wingtip vortices. So wing fences, yeah. A vortilon is essentially, it's a fence on the lower surface of the wing. What happens when we get to a particular angle of attack, that vortilon is going to create turbulence over the upper surface of the wing. Yeah, so again, it's having that same effect, but with most large aircraft, we can use the vortilon and hanging the engine off it. So the engine pylon acts as a vortilon for your larger aircraft. Ding, ding, ding. Yeah, small fence structure undersurface extends in front of the wing. High angles of attack generates a vortex over the upper surface. So we can use the engine mountings for that purpose. What I did forget to mention on the vortex generators, they come in pairs. Yeah, and they're sometimes detached from the aircraft because they're only glued on. If you do lose a vortex generator, we might be allowed to fly with 1 or 2 missing. The way we'll find that out is to look in the MEL. Yeah, so if you've lost one, have a look in the MEL, and that will tell you whether you can fly without. Sawtooth leading edge, exactly the same sort of thing. The sharp change in section of the wing is helping to keep the airflow flowing in the chordwise direction. It's preventing it from sliding off in the spanwise direction. Yeah. The sudden change of chord as well causes a strong trailing edge vortex. So you again your trailing edge vortex, you're keeping that boundary layer attached for longer. And again, that's just there. It's a good example of the sharp changes in section on the wingtip, and that is known as a sawtooth. Yeah, and it's just going to keep the airflow, give us that vortex at the trailing edge, so that the boundary layer is going to be attached for longer. Is that okay? Where's he gone? Chiranjeevi?
Okay, thank you very much, Jim.
Okay. Has anybody else got anything at all that they want me to revisit from this morning?
Hello, Jim. Did we cover this paragraph, control surface bias?
Probably not, because I was going to look at that tomorrow when we do powered flying controls. But yeah, just
it's okay, Jim. Then we'll look at tomorrow. Control surface bias, and there is one more, flying fouls.
There's one more what? Flying
fouls. There's one more paragraph.
Yeah, we've done flying fault. A flying fault is the tendency of the aircraft to yaw, fly nose or tail heavy, or one wing low. Yeah, and all that is doing is just saying some of the faults that are some of the conditions that could cause a flying fault. The control surface bias, yeah, when we look at power controls tomorrow, what we're saying is that a trim tab above certain speeds, above certain weights of aircraft, aerodynamically, a trim tab won't work. Yeah. So the only way of trimming the aircraft is to actually move the whole control surface. Moving the whole control surface, rather than positioning the control surface with a tab, we're positioning the thing hydraulically. So we'll cover more of that when we do hydraulics in the flying controls.
Okay, Jim.
I think I've covered everything else. I've gone through pretty much page by page. Yeah, mass balance. I can't see anything there. And then what we'll do tomorrow, we'll have a look at high-speed flight and the consequences and the effects of high-speed flight. We'll do that tomorrow. I don't really want to do it today because time's creeping on. We've done quite a bit, and if we try and push too much in, especially with high-speed flight, it's just going to get very tiring and very confusing. So you're just going to have to trust me on this one. We're better off finishing now and doing high-speed flight in the morning, and then we can have a look at the basic controls tomorrow afternoon, how we're going to operate them. There's a lot of duplication between what we've done today and what we'll see in the next book. This book is the theory of flight, how it should work. Tomorrow's book is how we're actually going to put that theory into practice, the mechanics of it. So unless anybody has got any questions for me, we will call it a day there. That will give you plenty of time to have a read through your notes. Yeah?
Jim, I have one question. Is that mass balance is working as a vibration damper for the control system? Control surface?
Yeah. Yeah,
It's like
essentially.
a vibration damper.
Just yeah, with our control surface, yeah, let's say it's an elevator or an aileron. Yeah, the hinge line tends to be round about here. Yeah, so you've got an awful lot of area behind the hinge line. Yeah, what happens as speed builds up? Yeah, the trailing edge will start to vibrate, it'll start to flip up and down, and that is known as flutter. Yeah, and if you allow that flutter to continue, the vibrations, the oscillations are just going to get bigger and bigger and bigger. So what we need to do is to put a weight as near as we possibly can to the hinge point. In effect, what we do is put the weight forward of the hinge line, and now that prevents that that flutter from kicking in. So the various ways we can put those weights on, we can put weights inside the leading edge, yeah, or we could put the weight forward of the hinge line by an arm, yeah, just put a wire forward of the hinge line, or on certain aircraft, yeah, they've got the horn effect, yeah, so we'll put a balance weight in the horn, and that brings us forward of the hinge line as well, yeah, and that's going to prevent the flutter from setting in at the trailing edge. Okay with that?
Okay, Jim. Okay.
You sure? Anybody else got any questions? Right, I'm just going to stop sharing just for a second, because include computer sound. Haha. Right. Bear with me. Right. Tell me if you can hear the sound as this plays, if you would.
Yes, I can hear you.
You can hear that music, can you?
Only your sound, not the music.
You can't see
No
the picture.
music. No music.
What could we see and hear that then?
We can see, but we cannot hear.
You couldn't hear the music playing?
Yes.
Right, okay.
Just play the video so that we can confirm.
Yeah,
I have sent the link.
I'll try and work that one out. Like I said, we won't lose anything if I can't get the music play. Well, it's not music; it's commentary. But I'll I'll have a word with one of my colleagues and see if there's a way around it. So you were seeing the picture, but you weren't getting any sound. Is that right?
No, we are not seeing any picture. We are seeing you only.
You are
And
not
no
sharing
sound.
the screen, Jim. You are not sharing the screen now.
Right.
No.
Can you see that YouTube thing on there now?
Yeah. Now we can see
And if
that.
I press play,
just hit the button, play button.
Can you see the picture?
Yes, now we can hear the sound.
Yeah, now we can hear the sound.
And you can hear the sound as well.
Yes, we can hear the sound.
Well, that's good then. We could be on a winner then. You might get a film tomorrow.
Okay, Jim.
Right.
Okay, sounds good.
Is everybody okay with what we've done today then? Is everybody happy with what we've done today?
Yes, Jim.
So far, yeah. If need to ask, we'll ask tomorrow.
Okay then. Right. Well, if nobody's got any objections, we'll call it a day there. Well done. That was a really good slog, that one. We'll do the high-speed flight tomorrow. We'll run through the video. We'll run through the rest of that book. And then we'll take tomorrow afternoon from wherever we get to. Bingo. Right.
Okay.
Okay,
Thank you, Jim. Goodbye.
I'll send some questions out, but don't worry about the high speed side of it because we haven't done that yet. Okay then, guys. I will see you in the morning. Take care. Enjoy your evening.
Okay, Jim. Have a good day today.
Okay. Cheers for now.
Hello, Jim.
Yeah.
Are you also going to cover electrical and basic avionics and instrument parts?
No, I'm just mechanical.
Oh. Okay. Okay, Jim. See you tomorrow. Thank you very much.
Okay, will do. Take care.
Bye. Mr. Jim.
Yeah.
So at last of the lecture, can we have the revision question like you did in aerodynamics? You remember in aerodynamics you kept asking some questions.
Yeah, I'll see what I can do.
So it will refresh us, you know, if you will keep asking some questions. It was so helpful in aerodynamics.
Yeah, it's. I'll see what I can do. I'll try. It's a bit awkward when when we're doing it this way, because in a class you can just point to somebody and ask them for the answer. But I'll see what I can do. I'll see if I can work something out.
See, now we do not have any option, Jim. This is the last option. The internet world.
Yeah. Oh, I'm well aware of that. Yeah, but what I'm saying is it won't work. In a classroom, I could just point to somebody, and if they haven't answered, I can point to somebody else. With this setup, it's a bit more difficult, but I'll try and I'll see what I can do.
All right, Jim.
Yeah.
It will be so thankful.
Yeah, like I said, chances are you'll have already had the questions, because my question bank is what you've got. I've given you all my material, but we can go through and ask those questions and make sure that people have got the right answers.
Okay.
Yeah. Yes, I can work out something like that. Yeah, yeah.
Okay, Jim.